Okay. Good afternoon, everybody. First of all, welcome especially to those of us outside of our classrooms. So faculty, fellow students, very happy when fellow students come to these type of events to support their colleagues. It's really, I think it does them a great deal to boost their sense of accomplishment and their confidence. And also thank you to some of our clients who've come all the way up from Washington, D.C. We really, really appreciate that. And our students do as well. So thank you very much. We're going to see 5 different presentations today. And each project is unique. And these projects change year to year. And I want to tell those of you who are tuning in via Zoom, whether you're clients or just interested parties, family members, things like that, or are those of you who are in attendance who may not be familiar with what this class is and what you're about to see, I'll tell you a little bit about the MUSA Client Practicum. So first of all, this class is taught by myself, Michael Fichman, and lecturer Matt Harris. Matt is the senior, I'm going to get his title wrong, but the Senior Data Solutions Architect for Snowflake, which is a major data analytics corporation. And because of his fantastic title, that means Matt is subject to sometimes getting whisked away to deal with urgent client matters. So to those of you students, Matt wrote you a very nice note last night. He's very upset that he couldn't be here today, but he's looking forward to watching the video of these presentations and seeing all that you have done, providing you feedback and reviewing your deliverables and so on. And I know he and I are both incredibly proud of what you've accomplished. I also want to note our TA, Nev. Where's Nev? Hi, Nev. Nev did a ton with Patrick Bransfield, who's also in the back to set up this event. Nev's done a lot of the logistics throughout the semester for our class. So this class is in the Master of Urban Spatial Analytics program, Department of City and Regional Planning here at the Weitzman School of Design at the University of Pennsylvania. The program, the MUSA program, trains applied social scientists to use geospatial technologies and methods. We really specialize in questions that start with where. It's a 1-year master's program, and many of our students go on to work in government and with NGOs using data to support decision-making. So we're distinct from an analytics program that you might find in a business school. And so when we're looking for ways to bring the classroom and the field closer together and give our students the type of skills and experiences that they need to be successful in the workforce, we developed, my late colleague Ken Steiff, and along with me, and then later Matt Harris, the MUSA Client Practicum, this class. You can see all of the projects that our students have done since 2018 on our class website, and these projects will be up in a couple weeks after we review them and launch them to deployment on the web with technical reports, applications, and things of that nature. And these are proof of concept projects that are developed over the course of maybe 6 months, or in our case with DC Deputy Mayor for Education, like 2 years. They're developed over a long period of time, and they're sort of unique to the clients and often represent some kind of R&D that they're trying to do, or prototyping or exploration with what we call public sector data science use cases. So if you're familiar with the world of tech, a use case is the specific set of circumstances that drive the development of a technology solution. And we work with our students, and you'll see over the course of today that the public sector use cases are really, really different because there's so many different things to consider as far as bottom lines. So I'll give you an example. This is an application that some of our students developed for Office of Transportation Infrastructure and Sustainability for the city of Philadelphia and bicycle transit systems to try to cite new bike share stations. And if you're purely motivated by demand and profit, that would be one kind of logic. But to understand what does it mean to have equity of access, what does it mean to work inside of political constraints and budgetary constraints that are unique to the public sector and deal with public data sets that can be messy, is a whole different set of skills entirely. And that's what we work on in this class. So practicum goes back to 2018. We have 44 projects, including this year, across a wide variety of domains with NGOs and local governments and some larger scale governments as well. You don't have to, I'm not going to read you this slide, but this just gives you an idea of all the people that we've worked with over the years. And they're really, like, to me, I'm just incredibly grateful to the time and the data and the partnership that they lend us. You folks from DC are a great example of that. We've been talking for a number of years about doing this. There's a lot of care that goes into building these projects on the client side, and not all those people are here for us to appreciate, but I just want to say to all of them, thank you very much. And thank you for entrusting your data to us to do an educational experience. That's ultimately what this is. We're trying to do things that are good for our clients and good for the world, but it's an educational experience. So for our students, we try to give them this introduction to a professional setting. They learn to manage a project together in a team. That's actually, to me, one of the greatest outputs of this class is watching you all work together in teams in a really professional way. You have dedicated project managers, you have project management documents. You meet with your clients and you learn how to be a good professional representative of an organization and comport yourself in a professional way and make meeting agendas and these other things that I think will serve you well from having practiced here. You get to meet and network with your clients. Some people go on to work with their clients, build portfolio items. Of course, the number three, the important meat on the bone from a technical perspective here, we do a lot of applied machine learning, professional application design, and a lot of non-technical data communication, which is what you'll see today. So you'll probably hear about a lot of really obscure technological concepts and this model and that model and tuning hyperparameters and this, that, and the other. But hopefully it's communicated in a way that if you've never heard, if you don't even know what data science is, it's meaningful. For our clients, we have a good opportunity to help advance their programming and policy goals, experiment and prototype new projects, new approaches, play around with new data sets. And sometimes this is really important to help them overcome some limitations they might have with budget or personnel, where there are things they want to do but don't have the ability to do. And our students are really helpful in that regard. Not to mention, they get to interact with us and, we can help give them the expertise that we have as Matt and I as professionals, having worked on a number of these projects as well. And I didn't prompt him to say this at all. There was no money changed hands in exchange for this quote. But Jason Jones, who we've worked with on a number of projects from Greensboro, North Carolina, Guilford County, said this about the following client that we did for their human resources department. He said, "You are going to get the highest quality work, highest quality team from any university project." And I don't know if that's true or not, but if he thinks it's so, then I'll just have to agree. But I think that the work that our students do really backs that up. So lastly, I think that courses like this are really important for the university, especially when the role of the university is something that is up for, a lot of public discussion in this day and age. It promotes good relationships between professionals and students and brings the lessons of practice into the classroom and the insights of the classroom out into practice. It projects leadership from all of you that you're able to do new things. And you offer this to the world in an open source fashion, that if somebody wants to take your work and do something with it, they can, and you're not hoarding the knowledge or the good that you can do. You're putting it out there. So with that, we get to see the 8th edition of the MUSA Client Practicum. And I'll just briefly name our projects and our clients, and then we'll get to our first team. The first project is with the Office of the Deputy Mayor for Education, Government of the District of Columbia. It's called Aligning Educational Resources using matriculation forecasts. And this is with our guests who have come up the Amtrak line or maybe 95 to join us. The second project is called Optimizing Entitlement Assistance Outreach to Homeowners, and this is with the City of Philadelphia, Office of PhillyStat 360, which is run out of Mayor Sherrell's Parker's office, and the Office of Information Technology. The third, which is with the City of El Paso's Capital Improvements Planning Division, our longtime partner, Alex Hoffman, who I'm very grateful for his continued partnership with us, called Designing a Dynamically Priced Parking Management System. And this is effort in data-driven program design and policy design. Fourth, the District Department of Transportation, which is our second client of the year from DC, and the lab at DC, which is a data science group in the municipal government there, out of the mayor's office, I believe. Yes. It's a transportation-oriented project, estimating unobserved bicycle counts. And lastly, but certainly not least, a project from the City of Philadelphia Office of Transportation, Infrastructure, and Sustainability, also known as OTIS, called Envisioning Neighborhood Futures After the Chinatown Stitch, which is sort of a data storytelling project that also involves modeling and statistics and housing policy. So we have a great afternoon in store. We'll have 3 teams present to you, and then I think we'll take a short break and come back with the final 2. So first is aligning educational resources using matriculation forecasts. Team 1, please come on up.
Test. Good afternoon, everyone. We are the DC education team, consisting of Nev, Amy, Jingmiao, and myself, Jiayue. Our client is the DC Office of the Deputy Mayor for Education, DME in short, and we have been communicating with Rebecca and Rory. This is the agenda of our meeting, and without further ado, I'll introduce our project. So this is a map of Washington, D.C.'s elementary school zones and the public elementary schools. There are 2 types of public schools, DCPS and public charter. Public charter schools operate with more independence than DCPS, but still receive funding from the public school system. Hence, we focus on both schools. Imagine a child living in a school zone over here. They can either apply to a school that's within the school zone, or they can apply to a school that's outside of the school zone, such as here. The difference, so we call this in-boundary, and if they apply outside, it will be known as out-of-boundary. For DME, as school resources are allocated by enrollment numbers, a key question is how should they plan future allocations? This challenge is highlighted by 2 case studies. In Bancroft Elementary School, the school capacity was at 0 for 2 years due to school enrollment in boundary continues to rise while remaining constant for out of boundary. Similarly, in Van Ness School, there was a change in school capacity from 2021 to 2022. Student enrollment in boundary continues to rise, but for out of boundary, they remain relatively constant throughout this period. Inconsistency between school capacity and enrollment trend could be a challenge. Our task is to help DME forecast elementary school matriculation numbers, improving the current approach by accounting for exogenous factors in our forecasting. Ideally, we want to show student enrollment for each grade as well. The current approach is shown by this equation. As you see on the graph here, it tends to overpredict for low enrollment. Additionally, they can only predict for some and not all future grades. Our use case is therefore to let DME input a housing pipeline and demographic information into a data system and receive each school's matriculation predictions for incoming elementary students in a near future year. I will now hand over my time to Amy and Jingmiao, who will demonstrate our app.
Thank you. So we have created a dashboard that displays school enrollment number predictions by grade level. Applying this to our case studies, first for Bancroft Elementary School, we are able to predict close to the actual number of students compared to the business as usual methods. And similarly in Van Ness Elementary School, we also achieve a reasonable results, although there were some limitations due to the missing data issue. And now DME can access these predictions through our web application, the DME enrollment dashboard. Now let's jump into the app. So we can see that the map in the center displays all the elementary schools in DC. And on the left, you can select specific filters to make enrollment predictions. For example, you can choose school year, like school year 24 to 25, and also you can choose DCPS or public charter school sector filter, and narrow down to a selected ward. And when you click on single school, there is some information, including some basic information on the right, the information panel, and also the prediction of the number by grade here. And we hover on the number will also shows. And also here is the enrollment trends chart on the right side. And our second case study is the Weitzman Elementary School at the level. So how we utilize the school to type in the school name in the search box. And it will automatically zoom into the selected school. And we can see that there are some information about this school, and choose school year 25 to 26. And as we said just now, the 5th grade enrollment number is 55, which is in the reasonable range. But what if something changed over the years? Like maybe the construction permits number may change, and also maybe the school capacity may change. So don't worry, you can just predict the click the predict with scenario button, and it allows you to customize these variables. For example, you can change the cumulative construction permits and also the percentage change in school capacity. And the prediction results will also change. So how did we make these predictions compared to DME's current approach, which simply carry forward last year's enrollment in grade K to estimate this year's grade K plus 1? How is our model different? Under the traditional approach, only grade 5 allows for a 5-year prediction based on the kindergarten enrollment, which is from 5 years ago. But our approach enables 5-year predictions for all grades. So what additional data did we use in our modeling process? Next, Jiayue will answer these questions and walk you through some key data insights.
Okay, thanks, Jingmiao. So we were given enrollment data of each school, broken down by years, grade levels, and the census tract that each student live in. The first key insight is overall school enrollments fluctuate across time. For DCPS, we observe that there are periods of increase and decrease. For public charter schools, this number has been increasing consistently. The second insight is the presence of spatial factors which could reasonably influence school enrollment. The movement of professionals into DC has driven housing boom in DC, as shown by the large number of newly constructed units in this diagram. This could influence the demand for school amongst family and thus student enrollment numbers. We then selected these variables for our modeling. Imagine that we have a row of grade 1 students from Bancroft Elementary School in school year 2013 to 2014. The dependent variable is the total number of grade 1 students in Bancroft in school year 2018 to 2019. For temporal variables, we take school year because we want our model to generalize across time. For group level variables, we look at school facilities, the geographic location of each school, and the grade level of students. We select geographic location because some schools have different locations based on our data. For spatial variables, we look at the DC public school zones boundary and the wards. Finally, we have social economic variables. These were taken from ACS 5-year data as well as Open Data DC. We engineered social economic variables in two ways. The first method takes the census data from the school location. The second method averages census data of the census tract each student lives in. I will now hand over the time to Amy and Nev to discuss our model in greater details.
To improve upon these predictions, we used a generalized linear model to predict incoming elementary students in the near future year at each grade for each school per our use case. The key objectives we have for our model are to handle many predictors, avoid overfitting, and improve model generalizability. With this in mind, we created a panel data with 9,401 rows consisting of the variables that Joey showed. They were split into test and train data and fit data. We used the test and train data to train and validate our model across time, and we applied the GLMNet model to the fitted data to generate predictions. And here's how our model improves on the business as usual approach. As you can see, we have, first of all, more data points for each grade level across the different schools. More. And second, there is less overprediction at lower enrollments, which is where a large number of the data points lie. And here is an overview of our performance metrics. Our average root mean square error for all of our predictions is 9.6, which is within a reasonable range. And when we plot the errors between DCPS and public charter across the number of seats for each school facility, we find that the distribution of the root mean square error is relatively random and doesn't show much skewedness from one capacity to the other, suggesting that our model is generalizable across the two different school sectors and at different size facilities. Zooming into predictions across grade level, we find that errors tend to be lower for grades 2 to 5. This may be attributed to stability in enrollment, as most students tend to stay in the same school as they progress through elementary.
Thank you, Amy. And now, if we want to do a deeper dive into the RMSE by school facilities for the 2 years tested, we actually found that most RMSEs are pretty low throughout the landscape, but there's this one school that really emerged to us, which is the Eagle Academy Public Charter School. So this school's really high error rate can be attributed to its serious financial struggles, also declining enrollment across the recent years, as well as the school's sudden shutdown late 2024. This kind of abrupt changes is actually unpredictable by our current model, because what our model is trying to capture is like the more regular, slow, steady, but predictable scenario changes. Next slide. So overall, here's the strengths of our predictors. We found that the top 3 predictors by size of coefficients are total students in the base year, total students 1 year later than the base year, the school sector, as well as average household size in the census tract that the school is located in. The way to interpret the coefficients, just to give an example using total students in the base year, is that each additional student in the base year will add about 4 additional students 5 years later, all else constant. And as for the user input variables, which we have constructed our scenarios from, we can see that their coefficient is from low to moderate. However, they remain significant in generating prediction outcomes. And to take cumulative construction permits in the next 5 years, for example, although each added permit will slightly dip the enrollment 5 years later, OL's constant, this can be really significant in DCPS zones undergoing significant development pressures as well as gentrification. So in using our app to forecast enrollment and plan school resources for the future, we have the following recommendations for our client based on our strengths and limitations. First, we recommend incorporate qualitative consideration while picking the scenarios. Second, we also recommend that the current approach, which is a progression, can still be used in conjunction with our model, especially there are big public charter schools that you are aware of, or there are schools undergoing abrupt changes like the Eagles Academy. And third, our model depends on availability of open data and especially the census. So if our client do have the more regularly updated socioeconomic data within the department, please feel free to substitute those variables using the more frequently updated data. And next, we'll just conclude our journey. So here is a list of milestones that we have achieved in the past few months, which would not have been possible without the general support and guidance from our instructors, Professor Michael Fichman and Matt Harris, as well as our client representatives, Rebecca and Rory. We also took some funny but cherishable team memories with us. And as we accomplish our project here and move on to the next phase of our lives, on behalf of my team, we want to express our sincere gratitude to Michael, Matt, DME, and the Weitzman department. Thank you very much.
Thank you very much. Questions? We have about 10 minutes for questions from each group. I'd like to actually, if you would like the first shot at the floor for questions, you may have it. If you don't want, that's also okay. Okay. Other questions? John.
It's a very nice presentation. I have a few questions about the basic logic of your model. It seems very nice and very useful and pretty straightforward. But I wonder about two things. So you focused on elementary schools, I think because there are fixed catchment areas around the elementary school. If you live within one of those catchment areas, you go to that elementary school. Is that true?
Yes.
Well, what about the charters? How are the enrollments at the charters determined based on where you live or your income or anything like that?
Okay, so regarding how it works in terms of applying, so for DCPS, there's actually two ways that you can apply. So the first is if you apply to, for instance, you live in this school zone and you apply within here, you will get acceptance immediately. But if you were to apply to a school that's out of boundary, so for example, if you apply to a DCPS school that's over here, or if you apply to like a public charter school that's here, you will have to go through like a balloting process, and then based on based on the success rate of balloting, then you'll get acceptance. Otherwise, you might get rejected, and after you're rejected, you'll be allocated to perhaps like a school that's within your zone, or you have to go and apply for another school.
So how did you incorporate that balloting process into your model, and in particular the issue of school quality? So let's and this comes up all the time. Let's suppose you live in a district where, for whatever reason, the elementary school isn't of the quality that the parents want, and that the school district is unable to fix that school in the short term, and that leads parents in that district to apply to other schools, charters, that may or may not have capacity. So I'm not trying to trip you up or anything. These are sort of important issues in cities like Philadelphia, where there are tremendous and DC, where there's tremendous variation school to school in terms of both capacity and quality. So I'm just interested in how you tried to think about those issues.
So like in the data set that we were given, so we have like a breakdown of school enrollment by grades, as well as like where each student come from. So for instance, in grade 1, they will give like maybe 5 students were from a school zone, a census tract that's perhaps like here, and maybe from another school zone, the census tract will be, the student will be, let me clarify again. So we were given data of grade 1 students, for instance, and they would break it down by like which census tract these students come from. Sorry, can you just go back to the maps? Yeah. So for example, from the data we could have like 5 students from a census tract that's here. Now just take note that this is school zone boundaries, it's not a census tract. So we can have 5 students from census tract A, 6 students from census tract B, and maybe like 7 students from census tract C. So I think our logic was that if we were to use where each student come from, it's kind of similar to like where the school zones are, but then we also make use of perhaps like the census tract that each student come from, incorporating an ACS data of by each census tract that the students come from, and then we apply that to our model when we were doing the socioeconomic variable. So in some sense, it's like using census tract indirectly to represent like the school zones.
I want to add that we also did, when we were doing exploratory data analysis in a chart that isn't in this presentation, we just took it out. We did look at the spatial like origin destination maps of where students were going, especially we're particularly like we're looking at schools that were like almost at capacity, 90% or more utilization, and we found that like over time the enrollment patterns tend to so this is 2014. These are in and out of boundary enrollments. So if you could see, there's like these yellow to purple, and then there's purple to purple. Yellow to purple is someone staying in boundary. And in 2014, there was a lot more schools that were almost near capacity in these sort of things, but a lot of the issues were in enrollment and in boundary. Over time, there's sort of less of those higher capacity. These are only DCPS schools, also not the public charter schools, because since the public charter schools aren't bound by the same like lottery process, and they're also located in different areas. So over time, as more charter schools open, they open in these areas where the at capacity DCPS schools are fewer, and in these parts of the city district up here, over time is where those high enrollment keep increasing. But if a lot of these patterns are, especially we also looked at like not all schools, but the movement isn't super spread across space in terms of like the scale of the district. A lot of out of boundary students are from the next school boundary over, but I think something we were also dealing with too was that our initial data was a very large panel with very detailed, minute grade level information. And there was a concern about our final model is very aggregated because that is sensitive data, student data. So we can't, we weren't able to incorporate it in a way that made sense in time for there to be particularly in boundary or out of boundary. We just aggregated by school. But yeah, this is how we looked at the spatial patterns and how we consider it, but ultimately we chose to aggregate it in the interest of time and also navigating that data security issue.
So I'm really glad you put that slide up because it shows you're focusing on an issue that's super important, but that your earlier presentation didn't get to. You said early in your presentation that you wanted to avoid overfitting. You said you had 18 independent variables. You didn't. You showed us a few of them. I think there's probably some level of overfitting going on. You're not running out of degrees of freedom, but I think there's probably some level of overfitting going on. But I just want to suggest, I think this is a really great presentation and a wonderful opportunity to move forward in this. But you might think about other model structures, in particular when people have choices about where to shop or where to go to school. Some sort of gravity model is a better approach typically than a pure econometric model. A gravity model allows for accessibility or mobility or distance, but it also allows for other factors to come in, like school capacity and school quality. So I think you've done a really nice job with a really tough problem and a great presentation. But as you move forward, I think you might investigate some other model structures. Maybe you did. I don't know.
We actually did a literature review before picking which models we want to trial upon. So it's kind of a combination of lit review, but also trials and errors. So there's actually a very similar project published by the IES. I think that's the Institution for Educational Sciences that was launching a study for forecasting school enrollment here in Philadelphia public school districts. So they come to the conclusion that based on what they have tested, they tested like 4 models thus far. It's the GLMNAT based as well as the random forest based models. So we did try out those 2 as well as an XG boost data, extreme boost data. But for us, it turns out that the GLMNAT is actually the best model. And as for overfitting, we kind of did like a manual review of what variables avoid like putting absolute numbers, but also percentage numbers into the same model. But we also like for the GLMNAT, because it balances like lasso and ridge, and we actually set the mixture to 0.5. So that makes sure like our GLMNAT is throwing out some variables but retaining and penalizing, reducing the coefficient for the remaining variables. So that way that's why we mean by like we try to avoid overfit. And also, I think something that also went into our consideration of producing like kind of, because I think the distance, traveling mobility is a concern more on the students end. But for us, I feel we're acting as like the imaginary agents of like schools. So it's more about, so we didn't, or we don't have like in the interest of time and also the interest of scope, we didn't like take transportation into accountability, but definitely get your advice on there. Like if we have a, so how do you say, like demand side model, this is like more like, that is a supply side model. This is a demand side model because we are the supply side. Sorry, we are supply side because we're offering seats, but they are demand side. If we can have the perspective from the students to complement this, it could produce a very powerful narrative. But yes.
Yeah, that's a really good response. I just think sometimes when you're dealing with phenomena that are spatial and involve choices in space, you want to look past sort of standard goodness of fit measures, like the ones you had up here, root mean square, to look at measures that are a little more distributional in how they evaluate how well the model performs. So I think this is your response now was just great, but think about some other model structures, not just a standard sort of modified linear model. But really nice job.
Thank you for the comment.
Any other questions, Alex? We have time for a quick one more, and then we'll move to the next group.
So just to maybe reiterate a point that you had earlier, which predictors should your clients be focused on the most when thinking about how, like, when they should be concerned about future enrollments? What are the most important, like, location predictors, and then maybe a non-location based predictor that predicts for maybe DC as a whole?
Just based on the previous slide that's talking about coefficient, there actually could be multiple ways to approach this, depend on what our client want to focus on. So for example, overall, this is what overall like our model is showing towards the end. And definitely the more total students enrollment records you have, those just naturally become the strongest predictors for years in the future. However, the challenge is here, if we want to do long-term predictions at a 5-year range, a lot of like this later future-based variables, they're just not available. So another approach for our client is either for known case studies that they know this might not be working as well, like the large public charters, they could still leverage the progression method, or alternatively, if there are specific school facilities or even wards they want to focus on, as shown in our app, we do have that filter, and they can flexibly adjust to that. And these scenarios are more per the client request that was given to us at the start. So we do feel that the construction permits, which is a proxy for like the number of developments that's going to happen in the area, that's something which is a big concern to DC at the moment. So that's something they can qualitatively and also just like integrate into the prediction scenarios. But for the facility change, that's actually something that's controllable and plannable. So if that's their focus, then they should leverage this scenario input to generate the best, most efficient outcomes.
Thanks. Are these OLS coefficients from like
Yes,
the
it's a
exploratory
little,
models?
yeah, but it has been penalized, right?
What's that?
It has been penalized, so that's after the
Right. So
that.
interesting. Okay. All right. Thank you very much.
Thank you.
Okay. Our next group is Philly Stat 360, right? Okay. And I believe our clients, Kristen, Tim, Maggie, are you on the Zoom call?
I'm on the call. Kristen, this is Kristen, and Tim is also here. And Maggie will join us when she's out of her other meeting.
Okay, great. Thank you very much. So when they're finished, we'll give you the floor to ask questions if you like.
Great. Thank you so much.
Okay.
Okay, good afternoon, everyone. Today, our team will present our work on Philly Stat 360's initiative to optimize entitlement assistant outreach to Philadelphia homeowners. I'm Rachel. This is Claudia. First, we'd like to express our gratitude to our clients, Kristen Bray and Maggie White at Philly Stat 360 with the Mayor's Office of Philadelphia and Tim Haynes with the City of Philadelphia's Office of Innovation and Technology for the opportunity to work on this important endeavor. So let me start with an important problem facing the city. Many Philadelphia homeowners are missing out on a significant property tax savings because there is no systematic way to identify and reach those eligible for the homestead tax exemption program. For many residents, especially seniors and low-income families, this tax relief could mean the difference between keeping or losing their homes. Now that we've established the problem, let's explore our use case and how we aim to address this gap. Our project has two key objectives. So that Philly Stat 360 can first identify and locate homeowners that are most likely eligible for the exemption but not currently enrolled. And second, we want to provide actionable insights about where these properties are located, the demographics of tracts with target properties, and the associated costs and benefits of different outreach programs or different outreach approaches. Moving forward with deliverables, our team developed a predictive model that helps identify those likely eligible homeowners, and that model has been integrated into an interactive dashboard that will serve as an exploratory tool for strategic insights to maximize program enrollment. So some important background on property taxes in Philadelphia. The property tax rate is 1.3998% of the total property value, which is assessed yearly by the Office of Property Assessment. To put this in context of the homestead exemption, the exemption is, like I said, a significant tax relief program that reduces the taxable portion of a homeowner's property assessment up to $100,000. So that's a savings of about $1,400 annually. So some overview of Philadelphia properties and the homestead uptake. According to data from Open Data Philly, Philadelphia has over 580,000 properties, and of that, approximately 246,000 are currently enrolled in the program. This map gives us a general sense of how exemptions are distributed across the city, with City Center and West Philadelphia and North Philadelphia showing less uptake rates. Update rate can in part be explained by eligibility. To be eligible, homeowners must meet some basic criteria. They must live and own the property and use it as their primary residence, not use it exclusively for business purposes, and not currently be enrolled in another tax relief program. Tangled titles are also an important challenge to understand while analyzing this data set. A tangled title occurs when somebody effectively is functioning as a homeowner, but lacks the legal rights associated with it. The City of Philadelphia does offer a 3-year conditional homestead for residents in this situation. And this understanding is crucial because it helps us identify that there's a specific subset of homeowners who might need additional support. To illustrate our target group more clearly, we have 2 examples of why some eligible homeowners are not enrolled in the program. On the left, Julia Thompson faces a tangled title situation. She lives in the property owned by her father, who suddenly passed away. While she has not yet transferred the property to her name, she qualifies for the homestead exemption, allowing her to receive immediate tax relief while resolving legal ownership. On the right, Dave, a longtime homeowner, part of an immigrant community, has limited English proficiency, which might be limiting or preventing him from accessing the benefit. Here's a real-world example from our data set of a likely eligible property that is not currently enrolled. The home has the same mailing address as the property itself, indicating property owner occupancy. It underwent a family transfer in 2013, indicated by the sale price of $1. And all of its neighbors in the surrounding parcels are enrolled in the program, but this home is not. If they really are eligible for the program and successfully claim it, the homeowner could save about $1,400 annually. The significance of this project is that currently there's no focused or strategic efforts to identify and reach those homeowners who are enrolled in the homestead exemption. There are many homeowners like Dave and Julia who need to be accurately identified. Our use case to identify and efficiently outreach those missing out on the exemption is the foundation for our predictive model, as well as the app we have developed for the Office of Philly Stat 360. Claudia will explain these strategies we use to address the use case.
All right, so how are we going to figure out which are the properties you want to reach out to? So first, we predicted properties eligible for the exemption program. So every property has a number allocated to it, and this number is from 0 to 1, where 1 is where it's most likely eligible for the homestead exemption program. We're going to set a threshold, so let's say we put it at 0.5. All the properties with a number between 0.5 and 1 will then be categorized by us as eligible for the homestead exemption program. We then compared this to whether all the properties are currently enrolled or not currently enrolled in the program. So green for currently enrolled and red for not currently enrolled. So with our model, we have a threshold, we put it at 0.5. We have these amount of houses that we think should be eligible for the program. We check, are they already enrolled? So among those properties that are actually already currently enrolled in the program, our model managed to accurately identify 85.8% of these properties. And these red houses, where we think they're eligible but are not currently enrolled, these are our target outreach focus group, because these homeowners are probably going to be eligible. They could save $1,400 a year, but yet they're not enrolled into the program. So we want to reach out to them. So this is about approximately 75,000 properties at a 0.5 threshold. So how are we going to reach out to them? We propose 3 strategies. We have a direct mailing campaign, so that's sending out flyers to these homeowners, a door knocking campaigns where we bring canvassers down and get them to talk face-to-face with the homeowners, and lastly, community partnerships. So we're going to get people to come down and go talk to people in leaders in places of worship or community centers or libraries, and get these people who are very rooted in their neighborhood to really talk to the people that come to their church or come to their library, and also post about what this homestead exemption program is in their location. So I'm now going to present our dashboard. So this is our dashboard. Let's say I am a campaign manager and I've been tasked to figure out who I'm going to reach out to and how I'm going to do it. So with the dashboard, we have a pop-up. We explain briefly what exactly this dashboard is. We have a legend. So the yellow areas are going to be hot spots of properties that we want to reach out to. And we have a black and red legend here. So once you close the pop-up, you see the map here. The clusters of red points are properties that are not. And if we zoom in, you then get to see the individual properties and their parcels. So black properties are ones that are already in the program. They're not of our concern. What we really are interested in are the red points. So these points are based on the threshold. Now it's 0.7. That means that every property that has a number of a predicted probability of over 0.7 is going to be visible on this map, but yet they're not enrolled. So these are the homeowners we want to reach out to. If I hover over, you'll see this predicted probability. It's 0.76, which is why it appears. You see some property characteristics, like the average market value, whether the mailing address is the same or not. And if I click on it, you then see the census tract it's in and the neighborhood characteristics of the census tract. I'm going to point out one, dominant non-English language, Spanish. So this is going to be useful for, let's say, getting canvassers who are Spanish speaking. I can also go to the threshold and I can turn this slider a different direction. So let's say I have more budget. I'm going to have a more ambitious campaign because I want to reach out to more properties. I'm going to move it to 0.5. And that means there will be now more properties, 268 in this census tract that I could potentially reach out to in my outreach campaign because they might be eligible but are not enrolled in the program. So we have estimated costs and benefits of the outreach strategies. We're going to talk about this later in the presentation. But for now, if I click export selected addresses, you're going to see a CSV pop up there. That's the track geo ID and the threshold. And so if I click open this spreadsheet, you're going to see all of the addresses and all of the owner names of the people that we think could potentially be eligible but are not in the program yet. And this is going to be so useful for me as a campaign manager to then figure out, okay, I'm just going to send a direct mailing campaign to all of these addresses. So that's our dashboard. And I'm now going to have, more features. I forgot. We have this address is the one that Rachel shared earlier, Cleveland Street. If we open it, there's 0.83 predicted probability, so that matches and corresponds with what we shared earlier about the characteristics of this property in terms of it likely being eligible for the program. Another feature also is the community sites toggle. If you see, you can hover over it and you'll see it's a place of worship, it's a community center, it's a library, and these are potential spots for me as a campaign manager to to send my people down to reach out to the leaders in these locations. And now I'm going to pass it on to Wenjun.
So how were our predictions made? And I'll start with introducing the data set we use. Of course, our dependent variable is homestead exemption, and our independent variable, we divided them into 6 main categories. For example, from the transfer records, we export whether like transfer types, transfer values, and the time of records related to homestead exemption rates. And after test their correlation, we selected those variables have a high significance to use as the predictors in our model. And now we want to show some important predictor variables. First is mailing address consistency, because it means the homestead exemption's core eligibility factor, the owner occupancy. Like we filter property, which their mailing address is matched with its location. And we can see from this chart, those properties with matching mailing addresses are far more likely to have exemptions, just as showed the right green bar. And but many eligible properties still haven't claimed one, so the red bar would be our potential targets. So through explore over like 580,000 properties in Philly, except the mailing address, we also find some properties with homestead exemptions share some other certain characteristics, like exemptions holding properties cluster in census tracts with far fewer unpaid tax accounts, porting to more stable owner-occupied neighborhoods. And beyond that, these homes almost never transfer ownership within 2 years and seldom carry commercial or rental licenses. And while assessed at slightly lower values but exhibit much steadier market trends. So all of this data can not only help us discover our potential targets, but also allow us to think about why some properties have missed applying for their exemptions. And we also explore the data at the tract level, which help us better understand the demographic characteristics of properties with different exemption rate. Like these two maps show census tracts with high owner occupancy, but they're different in homestead exemption uptake. Like the red maps shows tracts has higher exemption uptake, and we also find that they always has higher white residents rate and also very low limited English proficiency rate. So this will also be an important variables in our model and also help us think about what our dashboard should focus on in the future. So based on our exploratory data analysis and also test their significance, of these are the data we will use in our model.
So using these key characteristics as predictive variables, we build a model to understand their impact on the exemption status. Then we use this model to predict on each properties, and those properties predicted as with exemption should be eligible for the program. For modeling, we split our whole data set into two parts, 3/4 for training and 1/4 for testing. We use the training data set to generate different models using different methods, and then we use the testing data set to test the performance of different models and identify the most accurate one. Using our best model, we predict on each properties. Then we looked into those properties that were predicted should be eligible for the exemption but not currently enrolled in the program, because these are the properties we want to focus to do outreach, because they may have some missed exemption opportunities. And the spatial analysis shows that those properties clustered in Southwest and North Philadelphia. It may show some potential barriers in these areas, such as limited to access to the information. We also do some analysis from demographic level across census tract. We see that the most things stay pretty constant. It shows that our model is pretty equitable overall, but we did notice that the areas with higher education or higher senior population tend to have high percentage of properties with missed exemption opportunities. And this means that people in these areas are more likely to get flagged in our model. So this may be because some true difference in eligibility. For example, those areas with higher education may indicate there are more college students who do not own their home, or the areas with higher senior population may reflect that people are less likely to access or aware they are eligible of exemption. But it is still important to monitor other groups so that they make sure they will not be left behind unintentionally. We also did some cost-benefit analysis. And according to the cost data, if we did a direct mailing campaign to the whole targeted properties, and the cost will be about $35,000. However, assuming only 5%, which is an average level post-outreach update, it can benefit homeowners in direct annual savings about $5 million. Furthermore, if a door knocking to the 12,000 properties in the two high potential clusters was employed, the cost is about $80,000, and the benefits about 10% level of post outreach, the benefit will about $1 million. So the benefit is large higher than the cost level. In the end, we want to show how our model effectively reduces and identifies the properties that need to be outreached. So we did a simple filter. It resulted in a very huge list of about 333,000 properties. Compared to this, our machine learning model can substantially narrow down the properties that need to be targeted and effectively use the limited resources. And also using the spatial analysis, we can do more targeted door knocking in Philadelphia. And that's our report, and thank you for listening. And we want to give our special thanks to Michael Fichman and Harris and our client for your support. And we are happy to answer any questions and listen for your feedback. Thank you.
Thank you very much. I'd like to ask your clients, if you're there, if you have any questions or comments for the team.
I would just say this is absolutely excellent. Thank you very, very much for your hard work on this, and we will definitely be using this in the field. Tim, I don't know if you have any questions?
You've echoed my thoughts, Kristen, and I'd be interested to see if anybody else in the room had any questions on the presentation too. I saw quite a bit of cell phones up taking pictures, so it seems like there's a lot of interest.
Okay, so Tim asks if there are questions or comments from the room. Alex.
Thank you. I just want to say I work with a lot of local governments, and I really, really like the accessibility of this project. I think I've lost a lot of friends talking about parcels and property taxes, but you guys have really pointed in a very fun and enlightening way. I think it's really hard sometimes to use kind of deeper statistical models or GIS methods, and then also be accessible. So I really appreciated you did that. I also really liked how you thought about the end user of the city and the residents and the different types of residents. I really like that you looked at the different obstacles for each resident as well. One critique I might have is it would have been interesting to see for those that have a higher probability of being accurate, maybe have a different campaign, like saying we have to do door knockers on those, like let's say top 10%. That might be one little improvement, but it's really hard to improve this. I really, really appreciated it. My last question is, how did you handle those tangled titles? Were those able to be displayed? I know you guys had a lot to work with, but it was really interesting that you guys found that a really weird pattern out.
Sure. Okay, so unfortunately, there's no data set on tangled titles. It's sort of a thing that just sort of like happens out in the wild, and there's not really a systematic way to track it down. We did come across in the literature review an interesting study where somebody was able to pull like death records to compare the names that were on the properties versus, you know, if that person had passed away, as a way to try to suss out you know, those tangled titles. But that's just something that, you know, we felt was worth mentioning, and that the city does have a conditional exemption for them. Hopefully through something like this and door knocking and getting on the ground, they may be able to kind of suss those out more organically. But yeah, thank you.
Wonderful. Well, thank you guys.
John.
Sure, other people. Interesting. I'm a homeowner. I actually used the exemption, so I really appreciate your efforts here on my behalf and others. One question and one comment, and the comment's more philosophical. The question is, you mentioned you had some spatial lag variables in there. I wasn't clear on what they were, but I would think you would want, I would think they would be the share of the properties within some threshold distance around each subject property that are currently using the homeowner's exemption or are not using it. Was that your spatial lag? And I wasn't clear, but I would think that would be a useful variable, which is the sort of, we call it the contagion effect. But when we're talking about public benefit behavior, contagion is often a very good thing. And so you want to try and incorporate that. So I thought your model was very creative. The philosophical thing is, sometimes when you're doing these sorts of projects and you pull together all the data, it really gives you an insight into thinking about the problem in a new way. And I think your model enabled me to think of, or your results enabled me to think about what you're trying to do in an entirely new way that might have some benefits to it, which is to say you're developing a probability model of people who don't make use of the exemption who could, which suggests to me that the exemption ought to be designed as an opt-out rather than an opt-in. It's currently an opt-in, which is to say, if you're eligible, take advantage of it. A different way of thinking about it is to say, okay, our model predicts that you should be using this, or you could be using this exemption. And therefore, when we send you your property tax bill based on our model, we're going to include the exemption in it, okay? And give you a break up front. And you just tell us if you meet, when you send in your property things, if you meet these criteria. And if you don't, next year, we won't include the exemption. And I think the reason I like this is all your methods to improve the exemption, door knocking and mail campaigns, they weren't that expensive, but they're probably not going to be very successful. On the other hand, sort of taking an opt-out approach is likely to meet your objective in a much more useful way. So to me, this was a great project because it got me thinking about what the nature of the problem is in a whole new way. So nice work.
You want to get philosophical? I'm happy to explore that with you.
Yeah, in our final model, we have two data about the spatial, and one is the longitude and latitude to identify the location of different properties, and another is spatial lag to show the clusters among the properties. Yes, it's all.
I just wanted to say, I think, I'm not too sure, but I think the reason why it might not be an opt-out system is because people might not realize that they should be opting out of it if they're renting out, and there's a lot of properties that are being rented out on a larger scale. And there are, for the tax exemption, there are already, although a small proportion, cases of fraud in the sense that people are applying for the exemption even though they're not actually eligible. If it's opt-out, there might be a huge proportion of people that should be opting out but are not opting out from it, and it's harder to then sieve through and try to get people to check whether people should be eligible. I don't know, it's iffy in terms of where, but I think it's a great idea.
I do like the opt-out idea. I do think that your one slide probably did show that exact thing you're just talking about, right? Where the addresses didn't match.
I will say that the part of this with the taxes, in general, it's kind of a balance. Like those tax dollars that are collected also go to our schools, and Philadelphia schools, they are in need of those dollars. So I think having people opt out may be kind of like a missed opportunity to collect tax dollars that the school system desperately needs. But I do like the idea of maybe if they're in the predictive model, when you send that tax bill, to go ahead and say, hey, you're predicted to do this, fill out this form, or scan this QR code, or just make it more accessible and in your face when you are going to pay those taxes. So I do appreciate that idea, and maybe the city can do something with that.
I would like to give our clients the last word on this, because I think this project is kind of unique in that this was initiated from the highest levels of the mayor's administration as a partnership between our program and the city, and it's a very action-oriented group who's also very knowledgeable. So I was curious, for the folks from Philly Stat 360 on the other line, would you like to opine or offer the final word on this presentation before we move to our next group?
Again, I would say this is incredibly excellent. I appreciate all of your work. You've given us a lot to think about with the question of opt-out versus opt-in. And you guys really had a robust understanding of the issues because you flagged the dueling policy concerns that government has to add. So kudos to you on doing that. I will be sharing this with the mayor. And I think that she would also be very, very impressed. She's a very data-driven mayor, and this is absolutely excellent. So that's, I think, my last word. Kudos. And thank you.
And I would add congratulations as well. I mean, you did a very good job. And I think a lot of your answers to the questions here have really hit the mark. Even drawing back to your one slide that showed addresses that match mailing versus physical location. and calling out the fact that there might be some there that are taking advantage of the program that shouldn't be. And getting that tax dollar collection is certainly a reason for the opt-in versus the opt-out. You're really hitting the mark. You have a really good understanding of the whole thing, and I wish that I had any kind of critical feedback for you, but I think you really have done a good job of hitting the mark here and identifying a lot of this. And obviously, with any predictive model like this, making sure you're using the word likely. Likely versus not likely is a strong effort, and that's something that we've certainly done at the city with some of our predictive models. And as Kristen said, I think the mayor will be interested in seeing this, and hopefully you have a chance to present it to her as well. So thank you again.
Thank you.
Thank you very much. Wonderful job. Okay, our next group is our El Paso group, talking about the most important subject in all of urban planning, parking.
Okay, good afternoon, everybody. I'm Sean. This is Tut, Macy, and Ryan, and we're here today to present about our project on a dynamically priced parking management system. But before we begin, I'd just like to thank our client, Alex Hoffman from the Capital Improvement Department, for his consistent support and guidance through this entire process. So let's get right into it. Here's the upshot. Parking supply and demand imbalances have caused shortages and surpluses in on-street parking across the city of El Paso. We identified that the existing undifferentiated parking pricing policy is insufficient to manage this demand. Therefore, we're here to propose a dynamic, data-driven pricing parking model to manage on-street parking in the city. So first, let's talk a little bit about El Paso. El Paso is a city in Texas that sits on the US-Mexico border along the Rio Grande. The city operates 3 major land ports and is a hub for international traffic. But the city has identified that there are some issues with the utilization of on-street parking in the city. We found 39% of all blocks in El Paso have an average occupancy below 25%. In fact, just 10 streets account for 20.7% of all park time in the city. So I think the stat's a little wrong, but it's 10 streets. That represents less than 5% of all streets, representing over 20% of all park time in the city. In summary, there's an imbalance between parking demand and parking supply. However, this imbalance is inherent to the nature of parking. Let's take a look at an example to talk about why. So in orange, I've got a street that is in the heart of the business district of El Paso. In this street, you can see that through the day, the parking demand ramps up as people go to work and people go and shop. In the evening, it falls gradually. Let's contrast this with the blue line, which represents a street in the heart of the entertainment district right across the ballpark. It ramps up slowly through the day and spikes even more on game nights. In summary, parking demand, people, are mobile, but parking supply is inherently immobile. We can't just move parking lots from one part of the city to another part. And like any other good and service, it's economics 101 at this point. You need to then use pricing if you want to manage the demand. And that's why setting the right price is essential for getting to, parking supply and parking demand to be balanced. So what's the right price? And now we're asking the right questions. However, it's a very difficult question to answer. What's an easier question to answer is, what does it look like when we set the right price? When we set the right price, we expect about 1 or 2 empty lots on every street so that anyone who wants to park can park. But all other lots should be occupied otherwise. And in El Paso, most blocks have 10 or less lots. So that more or less corresponds to an occupancy rate of 80%. And so that's our target. Let me summarize. This is exactly what our client has proposed for us. We're here to propose a dynamically priced parking system and design key performance indicators to support this management system. In summary, we're not going to answer the question exactly what's the right price. We're here to answer the question, how do we get to the right price? And everything my teammates cover from here on out will go towards answering that exact question.
Yeah, so to design our program, we looked at how other leading cities are currently managing their dynamic parking. The general process is pretty consistent. First, cities like Seattle and San Francisco will identify their study areas. Seattle defines larger pricing zones, while San Francisco adjusts based on block by block using real-time sensors. Second, cities like Boston and Los Angeles measure occupancy patterns across different times of day and days of week, collecting data either through sensors or manual counts. And third, they adjust parking prices based on occupancy, raising prices where streets are too full and lowering them where spaces are underused, a model successfully adopted in San Francisco's SF Park program. So for El Paso, we propose a very similar approach, but with some critical improvements. First, we create data-driven parking districts, grouping areas based on real occupancy patterns, not these arbitrary boundaries that we're seeing. This lets us help manage parking much more precisely street by street. Second, we leverage El Paso's existing meter data pipelines using real-time transaction data to monitor occupancy. Our method works efficiently even with the limited data, making it affordable and scalable without needing these expensive sensors. Finally, we use predictive modeling to adjust prices proactively, forecasting occupancy by time of day, day of week, and district. This allows El Paso to set smarter prices that stay ahead of demand, not just react to it. When designing dynamic pricing, cities can choose to set rates by individual street or by district. Street-based pricing can offer fine-grained control in some places, especially where block-by-block differences are dramatic. However, in El Paso, this presents some challenges. One, it can lead to patchwork of small adjustments that are harder for drivers to anticipate. And second, it would require frequent, detailed monitoring to separate short-term noise from real lasting trends. By comparison, district-based pricing offers advantages that align really well with El Paso's needs. It smooths out the random fluctuations and highlights consistent occupancy patterns. It creates a simpler, more predictive system for drivers. And lastly, it's more sustainable for the city staff to manage over time. By grouping streets into these data-driven districts, we can balance flexibility with clarity, helping El Paso deliver a smarter, more user-friendly dynamic pricing program. So traditionally, cities like El Paso have drawn parking districts based mainly on land use, like separating office areas from shopping areas. This left photo that we see here comes from El Paso's own studies. It's a really great starting point, and we follow some of the same ideas, but we take it a step further. Instead of guessing based on land use, we build data-driven districts using actual parking occupancy patterns. The right map shows how natural parking behaviors form smarter zones, grouping streets by where people actually park in the same way, not just on how the land is labeled on paper. By using these real-world patterns, we can set prices that are more accurate, more fair, and more effective at managing demand. Here's the real power of the data-driven approach. Each colored line shows how streets in the same cluster behave similarly across time and how different they are across each different cluster. On Wednesday and Saturday, you can see clear patterns. Some districts peak early and some peak later in the day. By grouping streets that behave the same way, we can set smarter, fairer prices that actually match when and where people are parking. Now that we've seen citywide trends, let's take a look at District 5, the Central Business District. This area shows moderate and consistent parking demand across both weekdays and weekends. There's a clear morning buildup, steady usage throughout the day, and it tapers off in the evening, both Saturday and Tuesday. This tells us that the area likely serves as a mix of office, retail, and entertainment usage, drawing people throughout the week. With this kind of stable all-week activity, we wouldn't want to rely on peak hour pricing alone. Instead, district-level pricing helps us match policy to this consistent demand, encouraging turnover, avoiding overpricing, and keeping access fair across time. Let's take a closer look at District 3, the government and industrial zone. We can see strong weekday surge in occupancy, likely tied to courthouse hours, public sector offices, and shift-based industrial work. By Saturday, demand drops dramatically. Most of these streets sit nearly empty. This kind of sharp weekday-only pattern is exactly why district-level pricing works. It lets us charge more when demand is real, but avoid overpricing when it's not. We can also think creatively about this. If these streets are empty on the weekends, why not repurpose them? Community events, vendors, or public spaces could all be options. These are the kinds of smart, flexible strategies that emerge when we group by demand and not just by land use.
So throughout this presentation, we've been throwing around a few terms about how we measure street utilization rates. So let's really take a minute to justify why. So we've primarily focused on studying the street occupancy rate. So this is the preferred definition by many cities. But we've also explored some other possible metrics. For example, time over capacity. This is a metric that measures not the proportion of lots that are being used, but the proportion of time where the lot is at high occupancy. So in the ideal case, we'd actually like to be in the bottom right corner. That's where we've got lots of occupancy, but very little time over capacity. However, we found that these are really just two sides of the same coin, as you can tell by the fitted curve. There are trade-offs. You can't just increase occupancy without trading over some time when you're going to be at high capacity. And that's why we've identified occupancy as the main metric for our program and predictive model.
Now, I'll get into step 3 of our process to price parking, adjusting prices with predictive modeling. Rather than investing in traffic sensors or expensive infrastructure, we propose using predictive models built off the data El Paso already collects. The city has a great deal of transaction records and historical occupancy information that can be used to help predict parking behavior. This approach allows us to forecast when parking will be over or underutilized throughout the city. If a district is predicted to be over 80% full at certain hours, we recommend raising prices during those times. If occupancy is predicted to be under 80% full, we can lower prices to encourage more use. I'll now hand it over to Tut to explain our app.
Now, I'd like to showcase our dashboard, and I think the best way to experience this dashboard is through a couple of scenarios. But before we get into it, I'd like you to imagine that you are a planner in charge of parking in the city of El Paso. Your role is to monitor the occupancy level, analyze parking data, and support the city in making parking-related decisions. On the initial page, we can see an overview of the parking occupancy across the city. Average occupancy across all streets in the city is hovering around 26%. For the year 2024, on-street parking has accounted for over 870 cases, and on average, from talk or time over capacity, we know that streets are at a high occupancy rate only 8% of the time. Right away, we can see that the city has sufficient parking all around. So now let's try out some scenarios. For the first scenario, suppose a city councilor comes to the department saying that their constituent are complaining that there is insufficient parking near the convention center. Despite them having paid for entry for an event, they are wasting 20 minutes cruising around the venue looking for parking. They want the city to install more on-street parking near the convention center in the entertainment district. Now, we'll first filter the current month, September, and filter to the entertainment district, which is District 2. And here we can see the average occupancy is around 23%, and that's pretty low. And only 6.5% of parking time is at high occupancy. That's also lower than the average rate. So are those residents just making it up? No. We can see from the heat map here, and if you click the info button, you can see that this is the peak hour from morning to afternoon, and then from Monday to Saturday. And here from the peak hour shows that the district is really quiet during most of the week. It's just on Saturday afternoon that demand suddenly spikes. On the line graph, you can see how there is an almost cyclical pattern, and it corresponds to these weekend spikes. So do we need to build new on-street lots just to handle weekend crowd? Perhaps not. We can consider increasing weekend prices to deter people from parking longer than they need to, as we can see that a lot of people park for over 2 hours. So we can also explore spreading out events through the week and lowering weekday prices instead to improve usage. Now, for the second scenario, let's suppose it's the end of September. Our boss needs to submit a report to the council on the current occupancy patterns and recommend price changes under the dynamic pricing program for October. Now, let's look at District 5, the CBD. Now, because we are trying to look forward into the future, we will need to get the result for our predictive model. So we're going to turn on predictive mode. Our model forecasts that this part of the city has relatively high occupancy through the week, particularly during the middle of the day. We forecast that most people will park for less than 90 minutes
Overall, even at its peak, it's at a healthy level of around 60%. This is not too low or too high. And so we can propose to keep price steady here. We can repeat this with all the district every month, and we can print out the dashboard as supporting evidence for our decisions. And all of this is possible because this dashboard gives us district level insight, not just into average occupancy, but when the pressure builds, how long people stay, and how it's likely to evolve. So instead of city-wide guess, we can fine-tune pricing district by district, month by month, and explain every move with confidence. Now I give back to Ryan to explain about the model.
Finally, I'll discuss our modeling process and how the model makes predictions. We used a linear regression model to predict parking demand using occupancy rate as our dependent variable. First, in order to capture how parking behavior is influenced by the surrounding environment, we incorporated spatial effects into the model. Rather than using a single model for the entire city, we decided to create individual models for each district. This approach allows us to better explain and predict occupancy patterns within each area, as my team members have already covered. For example, in District 1, the University District, we specifically accounted for proximity to key points of interest, such as the University of Texas and the Cincinnati Street Commercial Corridor. Including distance to these locations in our model helps us better understand behavior within the district, which improves the model's explanatory power across the district as a whole. Here, you can see the map of the University District with these key locations identified. In addition to spatial effects, we incorporated temporal effects into our model as well. This primarily focuses on the natural cycle in human behavior that influence parking demand. For example, we accounted for daily and weekly cycles in parking behavior, such as the variation in parking by day of the week. As you can see, this graph of yearly parking demand in El Paso illustrates the oscillation of parking demand throughout the city. These patterns tend to be relatively consistent over time, so by capturing them in the model, we can better predict typical fluctuations in occupancy throughout the week and across different times of the day. In summary, we created a three-step process to price parking in El Paso. First, we created data-driven parking districts. By grouping streets with similar characteristics, most importantly by location, we can identify how different districts have unique parking behavior. Next, we measured occupancy through existing data pipelines, allowing us to find an appropriate dependent variable for the model. Finally, we proposed to adjust prices with predictive modeling. This will help guide policymakers in adjusting prices in El Paso's parking districts. This leads me right into our last slide, our recommendations. Our first recommendation is a 6-month dynamic pricing pilot in the Uptown District, with prices adjusted monthly or quarterly based on real-time demand. The pilot data would then be used to build predictive models and test district-specific pricing strategies. Next, we recommend long-term parking reform by removing parking requirements in oversupplied areas and repurposing these underused spaces for public use. Finally, we recommend creating a public dashboard to share price changes and real-time occupancy data. This will help to show transparency and build community trust in these policy decisions. Thank you all for your time, and we now welcome any questions or other feedback you may have.
Thank you very much. I'm not sure Alex is with us today. Nev, is Alex in the meeting? Alex, are you in the meeting? Okay. He couldn't make it. Okay. So I'm going to play the role of Alex, or maybe ask Alex adjacent questions that he might have for you. So, okay. I'd like to know, given that you had very extensive conversations with both your client, but also other public agencies in El Paso about parking, transportation planning, and so on, can you explain why this is a project of interest, given conversations about planning land markets and how those things have to do with planning? Because I look at this and I say, like, oh, most of the city is underparked. Like, what's the big deal? Why am I worried about demand? How does this relate to other conversations that are happening there?
Yeah, so they face a very interesting problem. So they have a university in the Uptown District that we created. And at that university, they really do suffer from overparking, which is really interesting to see after like this entire presentation that they definitely have enough parking as a city. So that's why for our program, we decided that we think that it would be best if they started with Uptown and trying to implement parking within Uptown, because there are 2 specific streets within Uptown. I think the ones near the university are a key point of interest, and then some near like university bars and like, the life of, university. Those face severe overparking right now, and they're trying to figure out kind of what they can do to kind of dispel it to these other areas where there's obviously significant amounts of parking that are available. They have another interesting dynamic where their pricing right now is just $1 an hour for all parking. So they currently have, I don't know if we touched on that too much, but they currently have no dynamic pricing whatsoever. So they're starting from very much like the base of where they could, and they just want to figure out how they can utilize dynamic pricing to, 1, try and spread out that parking near the university area, and 2, utilize all this land that they do have. So it's very like they have like almost 2 separate problems: too much parking in like 5 of the districts, and then 1 district has like 2 streets where it's just like chaotic and they don't know how to figure out how to fix it. So from what we gathered, those are kind of their problems. And then when talking to Bridges Department, they also expressed that they want to, outside of these 2 problems, they are interested in creating an actual dynamic pricing for their city as a whole. So similar to how like Philadelphia has it, like they want to have something like that. The problem is they are very interesting how they're like, our districts I think are a great idea because they do have very different dynamics throughout their city. So you see like some streets in entertainment district, like for their baseball team, sometimes they have some issues with parking, and they want to capitalize on it by charging more for these areas, and then also fix the problem of why it is only 2 streets in El Paso so overparked and chaotic during times of day. Sam.
Thank you. Eric.
Thanks so much. I really enjoyed your presentation. I think the intro where you really set the kind of purpose of dynamic pricing was terrific. I thought the graphics were really great. Following up on Michael's point, looking at your data, nothing is hitting that 80% occupancy threshold. Oh, by the way, I really like the comparison of time over capacity. And I think that kind of shows that maybe there is a little bit of a problem some of the time. So even if the 2 match quite well, you might consider, shifting the measurement that you're using. All that said, I feel like your entire presentation was an argument in favor of block by block pricing as opposed to district pricing, even though you were making the opposite argument. And what you've just said at the end really confirmed that. It's 2 streets that are problematic, or there are areas of 2 streets. So the whole idea of dynamic pricing is you really want to get people off of those specific block faces and onto the adjacent block faces that don't have a parking problem. And so I would really encourage you to maybe reconsider whether district pricing makes sense and try to analyze the data on a block by block basis. Because if you can solve it just by, increasing the price on 1 block face and reducing it on the 2 adjacent block faces, that's likely a much simpler problem. You could do it, particularly if it's just a couple of streets, you could do it without even putting in an expensive dynamically managed pricing system. Same thing with events, right? You can get a schedule of events and do things mechanistically as opposed to dynamically. Then you're not forced to install expensive systems and do expensive measurements, because as you noted and as Michael noted, there's a lot of capacity.
I think something that's also very interesting about this project is we have so much information from El Paso themselves that's like it's hard to share everything obviously in one presentation, but originally we were doing street-based adjustments. However, our goal with this was you have district pricing. However, just in Uptown do you face the struggle of the 2 streets being overpopulated with cars. So our goal through the program was that, they do have those focus on those 2 streets. However, they still keep the district level pricing because with speaking through Bridges, their long-term goal is to update their meters and actually have a dynamic pricing system. While we don't have like the data or they don't have the infrastructure currently to implement this, it's more so like this is something they could take into the future. So it's interesting, like we agree they have that problem now, and yes, doing street-based would be beneficial for them for that specific problem. But in speaking with them, they definitely want like sort of like a long-term plan that they could have in the future. And we came up with district pricing purely because of like the dichotomy of the different districts and how the patterns work. We wanted to really focus it so they could see all the different patterns at once without having the whole city kind of jumbled together and all the statistics just jumbled in one. But yeah, originally we did have street level purely because of the 2 streets that do face that problem. But just through the process, we realized like kind of what they wanted and sort of shifted it based on that. However, in our markdown, we go into sort of, you know, the street level versus district, and if there were a shift, how that would look. So it's kind of like you could kind of go either way with it for sure.
Charlie, here you go.
Yep. I just want to say it was a really awesome presentation, a very clear and concise explanation of an important public policy question. 2 years ago, as a MUSA student, I had the pleasure of working with El Paso and Alex. And yeah, when you implement something like this of making people pay to park and pay more, you also have to have the carrot, in which case El Paso has been developing its bus rapid transit system with 4 new lines since 2010. So it does create an opportunity to add pricing like this. My question is, with the conversations you had with different groups in El Paso, do you have a sense of the political will to actually implement a policy like this? Typically, people don't really love when they have extra costs added to things that they didn't have to pay for before. So I'm curious if that came up.
So we've not managed to get exactly that idea, which is that we don't really have that clear of an idea of how much political will right now there is to change from okay, not too much from the people. From the policymaker side, they are under the impression that a change of about $3 to $5 right now is what is politically available. An interesting fact on this is that a lot of people are afraid when you start to say like, oh, we're going to be changing pricing. Pricing may go up on some streets. There's naturally a lot of resistance to that. The thing that actually has been shown in other examples, like in SF Park, typically it tends to be actually quite neutral because some streets will have their pricing actually go down while some of them go up. But obviously we feel a lot more resistance when someone says the price is going to go up rather than we're going to drop the price somewhere else. So yeah, but very valid point on that.
Last question, John.
Really a neat presentation. I really thought your setup at the beginning to explain this was really very clear and very terrific. And it's the sort of thing that if you gave it a public meeting, I think they would appreciate why paying more for parking, even in parts of El Paso, might actually make sense. So you sort of had me at hello, and I really appreciate that. Eric's point, why study El Paso? Well, sometimes what we call the Overton window, which is a public policy window of opportunity, sometimes to really do good work, just happens to come up and you should jump right through the window. Hopefully it's not on the 2nd or 3rd floor. I think you did a good job. I have 3 quick comments. First of all, as you were talking, I was looking for thinking about ways you could call your model the Shoup model, after Don Shoup, the UCLA professor who pioneered many of these ideas. And I got as far as S, strategic, and then I couldn't figure out how H fit in. I wish you had shown us one of your example models. I don't really understand. I understand what I think is the dependent variable. You did a good job explaining that. But I don't understand how the independent variables function at the district level. And I know that's a nerdy thing, but I think in a presentation like this, given your conclusions and arguments, you have to show us a few of the internal workings along the way. I don't know if you have a slide of them now. Last piece is this is again more about public policy. When we think about pricing from a sort of very superficial thing, we think about that alters consumer behavior. That is, it works on the demand side. But as my colleague Eric has written very poignantly, we also want to think about what the supply side opportunities are, which is to say permanently altering the supply of parking by either taking parking spaces out of existence or adding new parking spaces where they are needed. So not just asking consumers to respond, but asking the supply side to respond. From your work here, whether it's just in the university district or larger in El Paso, do you have any thoughts about what possible supply side responses might be?
Just a quick just follow up on that. I thought especially your third point was pretty much on the money on that. One of the motivating cases for why we're doing this project is right now, Alex is looking at pushing through a bill to the city council to look at reducing parking minimums in various parts of the city. And some of the findings that we have here is exactly targeted to support that argument of why we may not need so much parking minimums in various parts. So I thought exactly you were on the money on that one.
I had one more thing. And then something that's really interesting that actually Michael pointed out to us a few weeks ago is kind of like the land use part of this. Like, how do we shift this perspective of parking to maybe something else? And that's something that I got excited about with this. And like, I think in our markdown, we have explored it a lot more. Obviously wasn't a huge part of the presentation, but it was kind of like a last minute thing that we kind of realized could be added is like, what could they possibly do with this land outside of parking? And it is really interesting to see like some ideas. I know Michael provided us with like a few papers that kind of go over that. So we are looking into that to kind of give Alex like an idea maybe of like, you know, the next steps of what these parking spots could potentially be when they're just sitting empty. So, yeah.
Very much. I want to compliment you on being the first project we've ever had that is built around program design, which is a pretty high ask of a group that is in a one-year technical master's program. So I want to compliment you on all that you've brought to the all the learning you've done to gain these insights. So thank you. Great job. Okay. All right. Welcome back from intermission. We have two remaining groups for the day. And here is our group from the District Department of Transportation, our second Washington, D.C. client. So please take it away.
So hi, everyone. Welcome back. We are the bike counts team in DC. And here's our lovely team. I'm Kuma, this is Hao, this is Shuya, and this is Xianlu. What the? Oh, here's our agenda of our presentation today. So first, we're going to talk about our use case, and then some data quality issues, and our lovely dashboard, and the most important thing, our model. So here's our lovely client, the District Department of Transportation and the lab at DC. So before talking about our use case, we're going to talk about our problem statement first. So while Washington, D.C. bike network is extensive, the current counter data is limited in both temporal and spatial coverage. So this limitation makes it challenging to fully understand cycling patterns and optimize network planning. To tackle this problem, DDoT would like to replicate and improve upon existing efforts by other cities like Oregon or Portland. So our use case is gonna be estimating and mapping bike counts in unrecorded locations across DC network over time. And by revealing the distribution and gaps in available data, our study highlights the opportunity to enhance monitoring strategies and guides targeted infrastructure improvements. So to go more detail about the key data challenges we faced and the corresponding modeling considerations, our team discovered that the data is collected in very different ways. So as we can see the map over here, the manual counters is counted annually only during the peak hour, and it has about over 100 locations in DC, and the time interval is very irregular, like 3 to 4 hours. And the map over here is the automatic counters. It contains only less than 20 total locations, but it has very continuous records, like every day, like 15 minutes time interval. So under this kind of circumstances, our target variable gonna be focused on estimating hourly bike counts for different segments in DC. And our approach of the model gonna be estimating spatial patterns with manual counts and temporal patterns from automated counts. So how could we, how does the temporal model work under this kind of like lack of temporal coverage?
Our team discovered that there's a twin peak trend typically observed in work commuter patterns. So it is safe that we assume that unknown location follow the same trend. As we can see all these charts over here, there's a very similar patterns. Besides these two model considerations, we also identify and incorporate other data sources like land use data, CABI data, and demographic data to strengthen our model performance. So I'll hand off Shuya to illustrate our beautiful dashboard about our detailed result of the models.
Okay, thank you. So let's explore how our dashboard helps reacting to our use case. So how do we estimate the bike traffic in areas without any count data? Our tool is designed for planners who want to fill in those data gaps and make smart decisions for bike infrastructure. You'll see that some segments have automatic or manual counters, but the majority have no counts at all. That's where our model comes in. It uses spatial and temporal pattern to generate predictions where data is missing. So firstly, we start with a quick instruction board. It helps new users get oriented and explains the key features we've built in. So as you can see, we've contained the key features like bike volume estimation, counterpoints, the characteristics of sensors, and also network metrics. And let's dive in. So based on our spatial model, we estimated the hourly bike volume for each segment. You'll notice we have pink and purple points on the map. They are automatic and manual counters. Even though most segments lack counters, the spatial model helps us estimate the average hourly bike volume across the network. So if a user selects a specific segment, they can dive deeper, and as you can see, this segment, it has no counter at all, but we can still get an estimation of 27 average riders per hour. And also, if our users want to conduct a comparative analysis, they can also check that. And for example, this segment has relatively lower median income here. So they can make a comparison of the local socioeconomic condition. And also, based on our temporal model, planners can also check about the hourly flow between weekdays and weekends, and they better look at the peak hour usage. So it helps understanding peak usage times and planning the infrastructure accordingly. Let's walk through a specific example. Take T Street Northwest as example, which have no counters at all, is a moderately connected mixed-use street segment in a high-income transit-oriented neighborhood with fair pavement conditions and young, educated, renter-heavy population. How do we know how many riders passing there every day? Our model pulls together all the relevant features. So this segment is located in the U Street neighborhood and is projected to carry an average of 26 riders per hour. As you can see, we can also see the comparative analysis here. And temporally, its flow pattern shows consistent hourly bike volumes. And also, if the user want to check about the street level imagery for environmental sensing, it's clearly a bike-friendly environment here. As you can see the bike signs on the road. And Xianlu will help you understand the model behind our estimation.
Thank you for helping share our lovely dashboard. So some of you folks today are likely more interested in what goes into producing these hourly estimates and solving the problem with data sparsity where we do not have counts for most segments in DC. However, we are required to estimate hourly estimates for unknown locations without past data. So how do we do this? So recall that most locations, they follow a twin peak trend, which means we can use peak hour spatial patterns estimated by manual counts to supplement the model for estimating hourly traffic from automated counters as such, where we take the hourly counts as a function of volume or the magnitude at each location and the temporal variation at its location. So to do so, we first join all data and predictors to segments, including trails and lanes. Then we train a model to predict peak hour counts from manual count data and spatial predictors. This allows us to estimate counts for every segment based on the spatial model, which is then placed into a temporal model trained based on automated counter data, which is supplemented with other time-based data sources such as capital bike share to obtain predictions for hourly bike counts for each and every segment in DC, which is what serves as a basis for our very beautiful dashboard. So, okay, so all of this seems rather abstract. So let me illustrate this workflow in detail. So recall that the sparsity of automated counters, which is colored in orange, means that there's insufficient spatial information from records to generalize to unseen locations. So this requires us to predict hourly counts with a two-stage process, where we first utilize the wider spatial coverage of manual counters, colored in pink, to predict peak hour counts. And these manual counts are counted in over 100 locations, but suffer from irregularity of intervals and days. Thus, additional predictors such as land use characteristics, path characteristics, and measures of connectivity and also census characteristics are included as part of the model to augment its explanatory power. So the resultant output, colored in lilac, is the predicted hourly bike count across all segments during peak hours. And this is used in the temporal model in order to model the hourly bike counts across all locations. So how do we test for this is by using automated counts, which are available in less than 20 locations, but they are present in 15-minute intervals. And we also use additional predictors such as hours and days of weeks, fixed effects, and so capital bike share estimates and a kernel density estimate of manual counts in order to produce an estimate for the predicted hourly bike count at different locations across the day. So based off our rigorous testing, we found that tree-based models such as XGBoost and also random forest regressors perform much better than regression models with lower errors for both types of models. So this is unsurprising because tree-based models account for interactive relationships such as the complex interactions between location and hours of day, which cannot be easily accounted for by a linear model. So what predictors do we use? So based on existing studies within Portland, Bend, Charlotte, and Dallas, we identified broad predictive categories associated with bike counts and also alternative data sets specific to DC. So this involves street characteristics such as pavement condition, bike lane width, and land use, among other things, network characteristics such as various centrality measures that we created, and also demographics such as population, education, and also like medium household income. And this is placed with spatial fixed effects such as block groups and wards, and also like time-based fixed effects such as hours and days of weeks. So in order to also supplement data gaps, we also utilize capital bike share data by deriving counts from reconstructing origin destination data into like segment-specific counts, and so calculating the volume at each nearest station for each segment. And we also use the kernel density estimate using manual counts. So after all this talk, our final model configurations are as such. The spatial model includes street characteristics, centrality measures, demographics, and we also found that wards perform better as grouping variables. For the temporal model, we have hours, time of day, wards, and spatial predictors, and sort of KD from auto counters. So interestingly, while the capital bike share data is rich in data, we found that it tends to lead to overfitted and poor models, and hence excluded from both models. So as a result, we were able to produce a prediction of hourly bike counts at each and every location in DC. So after all this talk, how does our model perform? So we found that our peak hour static estimates are more accurate than existing estimates made in other cities. So as you can see, we have a MAP, a mean average percentage error of 55, which is much lower than most cities. So this means that on average, our model is more accurate as a percentage of its true values compared to what existing workflows by other cities. So our model also performs exceptionally well in high volume locales, which is very important as high volume locales tend to be of significance for most traffic planning because it's where we have load. So even our hourly dynamic estimates are comparable with existing static estimates, and this is also especially accurate within high volume areas. So having covered the model performance, I'll now pass on the time to how to discuss its generalizability in applications.
Looking at the distribution of our model's performance geographically, we can see that our spatial model achieves its highest accuracy when predicting bike lanes within the central business district. On this map, the darker dots represent locations with lower error rates, clearly concentrated in the CBD district. Building on the spatial strengths of our model, our temporal prediction also show a distinct pattern of accuracy. Our temporal model performs best during the daytime peak hours with significantly lower error rates between 7 to 10 a.m. and 4 to 7 p.m. The blue bars shows average flow count throughout the day, while the red bars represent the mean absolute percentage area. Notice how the error rates decrease substantially during precisely the hour when cycling volume are the highest. This is particularly valuable because daytime peak hour are when bike lanes operate near capacity, and then when planning decisions have the greatest impact on cyclist safety and efficiency. Given these performance characteristics, it is important to clarify the practical application of our model. To recall our use case, we aim to provide an overview of bike commuting patterns and infrastructure utilization during critical time period, which may help support planning decision at city level scale. However, we want to be very transparent about limitations as well. This model is not designed to provide real-time, extremely granular, or perfectly realistic representation of cyclist volume down to the individual riders. Rather, it is a planning tool that captures broader patterns and trends to guide infrastructure development. Beyond technical performance, we also evaluated our model throughout an equity lens. An important consideration for any urban planning tool is whether it performs equally well across different communities. Interestingly, our analysis shows that our model actually performs better within the minority populated areas with lower error rates on average compared to majority white areas. To allow us exploring such relationship with demographic and equity, our dashboard features a comprehensive census data panel that allows planners to visualize various demographic indicators alongside cycling patterns, enable them to identify potential equity gaps. Based on our experience developing this model and dashboard, we have several recommendations to improve future data collections and analysis efforts. First, strategically placement of more automatic counters across DC's diverse neighborhoods to enhance predictions accuracy in unmeasured areas. Second, implement constant count timing protocols to establish reliable baseline data that accurately captures true cycling patterns. Lastly, our primary model works best for busy bike lanes during peak hours, but we've developed alternative versions that may help better serve specific planning scenario or less travel areas. So we'd like to extend our sincere thanks to our client, DDOT, and Lab at DC for their collaboration and data access throughout this project. We are also very grateful to our instructor, Michael Fichman and Matthew Harris for their guidance and feedback on every stage of the development. We are now happy to answer any question you might have.
Thank you. I believe we have Jack from DDOT in the meeting. Is that so? Jack, are you there? Maybe, maybe not. Okay. I thought I saw Jack there earlier. Is that Jack Crum? Ellie Moore, hello.
Jack was trying to speak, but I guess you couldn't hear him.
Okay, well, the floor is yours for any comments or questions you might have.
All right, we also have Marshall, but Marshall just hopped on, so he missed the presentation. I think, you know, I'm not very familiar with the metric that you used for evaluation. It was interesting to see the comparison with other jurisdictions. But the sort of takeaway that the model is most accurate for segments with high volumes. I would think that that seems likely for sort of any iteration of the model if one of the reasons we might place a counter in any particular location is because we have high volumes in that location, that sort of our ground truth data is most similar to segments with high volumes. Did you do sort of any analysis or kind of look at that question at all?
Sorry, would you mind repeating like your question again?
Yeah, just wouldn't we think that the model would be the most accurate for segments with high volumes? Because those are the most similar to the segments where we have counters. So sort of you're finding that your error rates were lowest for segments with high volumes. Seems potentially sort of what we would expect to find just based on where we place counters.
Okay, I guess like maybe it might be useful for us to like explain how we train the models and test its performance. So for the spatial model, what we did was, okay, so as you would know, like this for the manual counters, the spatial coverage of the manual counters is much more diverse, and I think it's also placed in locations that do not have like very high flow rates. So what we actually did in testing the spatial model was actually to firstly separate it into like a train and test data set. So this was fairly random. So it had a good mix of locations with high and low volume counts. So afterwards, we went on to like test the model via a K4 validation process. So this was also done based off locational grouping factors. So I think as far as whether the observation that the model performs in high volume locations is accurate, I think it's pretty fair to say that it's quite accurate for the spatial model. However, for the temporal model, because we only had 20 locations, it didn't quite make sense for us to do the same kind of train test split where we selected certain locations as a testing data set, because that would leave us with far too little data to actually make any any proper performance testing and to actually probably train a model. But what we did was actually, so we took the last week of each month as a test data set. But in our cross-validation process, we did specify different wards and different like block groups as ways to kind of make sure that the model is applicable across different locations. So while we are unable to actually test whether this performance actually applies to locations where you do not have data, I think like what could be done in the future is probably to collect data in new locations, particularly using automated counters, and then maybe run a few like placebo tests and actually testing whether this model built with the existing data is applicable, like whether it's accurate in these new locations. So yeah, I think like one of the key challenges we had, which like admittedly was what you wanted us to solve, is really the data sparsity of the automated counters. So yeah, I hope that what we have is useful, and yeah, and I hope this answers your question. Thank you.
And can you, sorry, my audio is not working, so I'm worth through Nelly's audio. I have two questions. The first is, did you explore the feature importance for the different segments? I'd be curious what variables contributed to a higher or lower predicted count. And the second question is, did you look into any type sort of confidence intervals for your predictions? So we have such a low count. I'm curious how confident those predictions were.
Okay, we did actually look at the feature importance, but because in the interest of time, we did not actually add it in the slides. But off the top of my head, what I recall is that, interestingly, actually like demographic variables was actually quite a strong predictor for the spatial model. And for the temporal model, because like basically what it had was a series of spatial features and hours, so naturally like time like the hours and like the time of day was like particularly important. As far as confidence intervals, like this will also be in the markdown that we'll provide you. So yeah.
Most of my questions will probably be answered in that. I have very, very specific questions that you don't have time for now.
You have an additional question?
No, Jack was just saying that he looks forward to reading that.
My questions are too specific for this meeting.
I totally understand.
Yeah.
May I ask if the assembled room has some questions? Eric, as our resident transportation professor, I should give you the first shot.
I appreciate it. Thank you, Michael. First, I thought this was terrific, really super interesting, really useful. I think has applications for traffic safety as well as kind of thinking about infrastructure. I'm particularly interested in going from the automated counters and getting estimates of the other like annual count locations throughout the city. And you've talked a little bit about kind of areas where you're predicting well, you've done a little digging into the model. Having done all that, I'm wondering, do you have a sense, just thinking about the unknown locations and their kind of variance over time, are there areas where you think you're doing, a better job predicting and areas where you're less confident once you get outside of kind of that central area where you have these points of comparison and you're just going completely unknown except for the predictor variables?
Well, I'm afraid that like I'm actually unable to answer your question because so the main problem with like the automated counts is that we only have 20 locations. So essentially, this is a modeling exercise that's pretty much an imputation exercise. We are trying to like input values where we do not have records. So to answer your question, a good way to actually estimate whether these values are in fact real would actually require something that is beyond my expertise as a urban analyst. And I think it's probably important here to highlight that as urban analysts, we sometimes we have to be frank with what the data can do. So frankly speaking, 20 locations, we can make an estimate based off a series of assumptions like the fact that different locations, they have similar variations across time, and hence we can use pick our magnitudes and kind of make a model to create this. But ultimately, I think what would be useful is really the ground expertise of how things vary across the city. And I think this is something that DDOT will probably have and would probably be able to comment on far better than we do, because none of us are local DC residents or local DC planners. But what we do have is a dashboard that allows you to kind of explore this data. So one of the considerations we did with our dashboard was to make a map that is a bit more generalized and shows a more area to area differences. So you can zoom in the areas you want to, but one of the decisions we made was to actually represent the data in a way that showcases how things vary more broadly across the city, and also to provide features such as showing different census characteristics, such as you can validate this with your own professional opinion expertise. So yeah, I think I'm unable to answer your question, but I hope this helps. Yeah.
Terrific answer. Thank you.
I just want to follow up on a few of Eric's questions. First of all, I just want to compliment you on your approach and your research design of treating the automatic counters and the manual counters differently throughout and using them to get different insights, complementary insights. I think it would have been very easy to just start by finding a way to combine them, in which case the noise from each of them is different and would have introduced some additional bias. And I thought it was very clever of you to keep them separated and to maximize what you could from each of them. So I think a lot of times, both problems and opportunities start at the research design phase, and I think you had a really strong research design. So thank you very much. To your model, I noticed in your spatial variables you had centrality. You didn't have network connectivity. There are two types of network connectivity. There's facility connectivity, and then there's actual pathway connectivity. In other words, is a bikeway on this street connected to a bikeway on another street? Did you try those? Did you experiment with those? Maybe you just didn't have the data. But I think they're very important. And I'll just tell you a story. Back in around 2005, the city of Copenhagen, which by the way, has a 50% bicycle mode split for work and school trips. It's the highest in the world, I think it is. That's not a Trump figure. I didn't just make it up. I think it's actually documentable. But back in the 2000s, they had about a 30% mode share, and they wanted to up it. And so they really focused on improving connectivity, facility connectivity. And that was the thing that improved their bicycle mode share the most, by saying, how do we get from one part of the city to another part by a series of complementary facilities. So I think connectivity ends up being extremely important. One last comment. Your model's going to overpredict and underpredict, and it's going to do so systematically based on what your model looked like. And this would, I think, what Eric was getting at. Have you given any thoughts about what you should or shouldn't do from a policy or a planning perspective in the places where the model might overpredict or where it might underpredict? In other words, some rules of thumb, like if the model overpredicts here, we should do this or not do this. If the model underpredicts, give any thought to that?
So in terms of like, so just to be clear, what you're trying to ask is like, is there any like specific guidelines with regards to using our models and the kind of planning decisions it can inform and the kinds that it cannot? Is that like, is that right? Okay, so in terms of what we can actually do with our model, so I think it's fair to kind of assume that this model would probably not be very useful for segment by segment level analysis where you're like, oh, this segment has 25 counts at 6 a.m. in the morning, and hence like it has this characteristic, so I'm gonna like build a buffer or something. So it's probably not so useful for this, but it's probably more useful for understanding like broadly across the day, like what are the kind of volumes of cyclists around the city, which may be hard to understand and also visualize and like make decisions when all you have is like a series of scattered counters. So I think like with regards to over and under prediction, and another important thing to consider is that another important thing to consider is that an error of maybe like 10 may not matter as much in like a high volume location with like thousands of riders per hour, but it will matter quite a lot in like areas with maybe like 8 riders. So like areas out in more rural locations, like with less infrastructure coverage and stuff like this. So what we actually did with our report was to sort of provide various measures, like in terms of absolute errors and also relative errors for comparison. So I think like this is the kind of things that would actually be helpful for DDOT in making like what they want to do. And because like from our understanding, they are in a rather like initial stages of utilizing this bike count data. And hence like when they first came to us, like there was quite a bit of confusion on our end on like what exactly do you want to use this bike count estimates for? So what we actually prioritized was kind of providing them options. So like options in terms of different models, like different model configurations, and also providing them information about what worked best in terms of like improving model performance, like whether stuff like external capital bike share data sets was useful in hopes that they can kind of use this to inform their future modeling processes with like data sets that they are unable to provide us for, you know, like privacy reasons and stuff like that. So I think like, yeah, I don't think that quite answers your question, but I hope that this is a sufficient response. So, yeah.
Yes, and also you did have a connectivity variables in your model, correct?
Yeah, so like centrality. So there was like 3 types of centrality measures we calculated, which I think like Kumar can.
Yeah.
So we have like 3 types of connectivities. The first is the degree centrality, and then it's betweenness, and then there is the closeness. So for the degree of the centrality, it's like how a node is directly connected to other nodes. And the betweenness, it's about like how often a node is follow the shortest path of every trails. And the closeness is about like how close of each nodes.
Yeah, those are good measures.
Mm-hmm.
If you want to push this work, Jeff, Bowen, and
Just
software package that runs the Python package runs
Mhm.
the Spatial,
Mhm.
which just generates all sorts of quantitative other measures.
Thank you.
Thanks for that recommendation. I want to, before I congratulate you and we move to our next group, I want to thank our partners in DC. That with DDOT, this is our second project with them. We did one in 2019, helping them with their launch their scooter system, and the lab at DC. This our second project with them. We did one of my favorite projects of all time, which was a vermin detection algorithm for local inspectors. So we really appreciate the partnership of all of our friends in Washington, D.C., obviously with 2 groups this year. So thank you very much. Congratulations to this group. This is a very creative project. So cheers. Okay, and last but certainly not least, we have our team from Office of Transportation, Infrastructure and Sustainability, City of Philadelphia, and their project related to Chinatown.
Okay. Hi, everyone. Our project is titled Envisioning Neighborhood Futures After the Chinatown Stage. And here's our team. I'm Yixuan.
I'm Aki. I'm Luli. I'm Sijia.
This is Ray.
And we'd like to thank our clients, Casey and Chris from Otis for bringing this project to us and for their continuing feedback and support. Okay, let's get an easy start. Have you ever been to Philadelphia Chinatown? And what does Chinatown look like in your impression? Is that looks like this? A thriving commercial hub with bubble tea, hot pot, and so many kind of delicious foods. But do you know this is also the Chinatown with almost no one there and like not blooming at all? So why such a big difference between the north and the south? Yes, it's because here's the highway I-676. It cuts through the Chinatown. And of course, as a community with resilience and dedication of cultural preservation, Chinatown has been putting continued efforts to fight against the urban renewal projects, also including the highway. And the residents are afraid of not being able to pay the rent. Even though they successfully protected the Holy Redeemer in rearranging of the highway, the expressway still cuts through the neighborhoods, displacing several businesses and the residents and create a physical barrier there. And here is what it looks like now. And to the north of the highway, it lies the Callaway, which is also suffering from the highway. The Callaway has evolved from an industrial zone into a neighborhood of the loft apartments and music venues and also the railway park. And despite the growth, it still contains active industrial sites and vacant lots there. So we come to 3 main concerns from the neighborhoods: the rising rent price, the physical price barrier, and also the less developed lands. And this brings to our project, the Chinatown Stage, which seeks to reconnect the Chinatown. It provides safer street design and more green spaces. And the first phase of the project has been allotted about $160 million and will cap the highway between 10th and 12th streets. Construction plans are set to start next year. And though Chinatown Stage seeks to repair harm and caps in the other cities, has increased the property values, and this threatens the local residents' ability to remain in their communities. So this is why Otis brought this project to us and to investigate the question, how will the Chinatown stage change the trajectory of this neighborhood's future? And we are tasked to explore how the Chinatown stage will change property price in the surrounding neighborhoods and the 3 hypothetical futures. And we also compile this to the information into a public-facing, data-driven story map to inform the current residents.
So in order to understand how the Chinatown stage, a cap that effectively removes the presence of the highway, could change property prices, we first need to understand the highway's effects on property prices themselves. So this is our study area. We go from Arch Street to Green Street, 6th to 17th Street with a total of 3.36 kilometers squared. We conduct this analysis of highway effects at 3 different scales. First, we look at the effect of the 4 main highways in Philadelphia on property prices within 500 meters of them. Then we zoom into our study area and look at specifically I-676 effects in our study area. Finally, we separate our study area into north and south to see how the highway effects are felt differently across different neighborhoods. For each scale of analysis, we report highway effects by discussing the change in predicted property price from 50 to 150 meters away from the highway, conceptualizing a block to be roughly 100 meters. We report this in absolute value of change as well as percent change. First, we start with the Philadelphia scale analysis. For 3 of the 4 main highways of the city, property price increases as one moves further from the highway, ranging from a 4.4 to 11.5% change per block. This is consistent with literature which states that in urban areas, property prices tend to increase as one gets further away from the highway because of air and noise pollution and barrier effects caused by the highway. The one exception to this is properties near I-95, where we see prices decrease by 10.7% as one moves a block further from the highway. We suspect that other factors, such as location preference on the east side of the city, are interfering with the expected highway effect. Neighborhoods like Old City, Queens Village, and Fishtown are home to many high-income Philadelphians who may have access to amenities that diminish the nuisance of nearby highways. This is our first inkling that highway effects might not be as strong as we expected them to be. Furthermore, zooming into our study area, we see a stronger and positive relationship between the distance to I-676 and property price. As we move 1 block further away from the highway, we expect property price to increase by about $43,000, which is a 13% change. When we control for some basic property features like number of bedrooms, bathrooms, quality grade, and zip code, moving a block further away from the highway still results in a $31,000 increase, or 11.8% change. Now we ask, does the highway effect change property price the same way in different neighborhoods? As you can see here, the answer is no. Though median property price hovers around $400,000 for both sides of the highway, on the north side, we basically see no highway effect, with only a $3,500 increase as one moves 1 block further north from the highway, or a 0.8% increase. On the other hand, price increases by $74,000 as one moves 1 block further south from the highway, or a 29.7% increase. You may wonder, why do we see a bigger effect in the south? We suspect that there are other factors on the south side that are inflating what we're calling the highway effect. One such factor is the distance to City Hall variable. On the south side, the City Hall and highway effects are opposite one another. On this side, as one moves further south or away from the highway, they also approach closer to City Hall, a marker for the central business district. This side of the highway also has a lot of CMX5 or Center City commercial mixed-use buildings, which tend to have higher prices. We cannot fully tease away how much of the highway effect may simply be explained by proximity to City Hall. However, on the north side, City Hall and highway effects are correlated as both the highway and City Hall are south of Callow Hill. Note that though the correlation between distance to City Hall and property price is close to null, it has a slightly positive relationship, possibly signifying that the highway almost nullifies the City Hall effect in the north. There is more industrial land in the north which may not be affected by proximity to the CBD as much. So in summary, we conclude the following points from these highway effect analyses. Property prices increase with increasing distance to highways. Proximity to City Hall, in the southern side of the Chinatown stitch, tends to increase property prices, probably due to better access to commercial services and other buildings. Highway effects, and lastly, highway effects are not as clear-cut as expected.
So next, we'll look at how our projects might help reduce the highway effects on property values. Now, let's work through the scenarios we modeled to understand how different interventions might shape the future of Chinatown. So scenario 0, as we've seen, is our current condition where nothing changes. The highway remains a physical and economic barrier dividing north and south Chinatown. A persistent pattern of spatial imbalances and property value exists. Scenario 1 introduces 3 caps. One becomes a park and the other 2 reconnect streets of both sides. These caps help store physical community, improve walkability. It's a starting point in our project to stabilize property values between the 2 sides and signals new possibility for future reinvestment. So to explore the future possibilities, we modeled scenario 2, building on the cap structure by changing zoning and land use. We convert part of vacant land, industrial parcels and single-family housings into either multifamily housing or commercial mixed-use properties. The goal here is to increase overall population density, expand affordable housing supply, strengthens commercial functions, and activates underutilized land parcels on both sides. While price patterns remain uneven in our scenarios, these scenarios does reduce some of the long-term effects of the highway currently has on property value and development opportunity. So next, we'll explore our scenarios through the experience of 2 target users to explore how each scenario may affect the sale price of the properties they care about. On the left is a business owner who runs a restaurant in Chinatown. He has been renting the property for 8 years. He cares about future rent trends for his own property and nearby housing affordability for alternate options, where he can invest to expand business. And he also cares about the street activity that affects customer flow. On the right is a renter living in Cow Hill, the north side of the highway. She is the newer to the neighborhoods. Her main concerns are whether she can continue to afford living here if the rents rise, and surrounding commercial area expansion that might affect her daily life and sense of community. Next, we'll explore the story map to see how different planning scenarios may affect each of their expectations.
This link navigates us to the future section of our story map. We also have the past and now section for background context, but this is what the user is mainly going to use it for. Here's a little recap and links to the scenarios we just talked about. And in this first section, this is the distribution of house price in scenario 0. And by clicking on any one of the properties, some basic information will show up, including the property ID, land use, zoning, as well as their price under this scenario. And then we have scenario 1 and scenario 2. Then for the next part, these sections covers the change in percentage of a certain property in the neighborhood. So for example, our business owner user might be interested in seeing, let's just say this is the commercial properties he rents, might be interested in seeing the price change percentage from scenario 0 compared to scenario 1. After seeing this, this can help him make better decisions on whether to continually renting this house this property or move to another location. By looking at other properties nearby, he may also be able to identify potential competitors in the future. And this is a section comparing scenario 0 to scenario 2. And then for our local residents, they might be interested in seeing the price change in your residential property. So after knowing that, they might be able to make better decisions on whether to stay at this property or move to another location. By filtering out different land type, they might also be they can also be informed about potential growth in commercial areas such as restaurant and grocery stores.
In addition to the user's experience, what else did we learn about how the Chinatown stage would change property prices? Based on our prediction, you can see that the property price increases about $100,000 generally after building the stage, and slightly increases about 10,000 when more restaurants and housing are emerging in the neighborhoods. Comparing changes in north and south, it shows that the Chinatown stage somewhat balances the city hall effects in the southern part and enhances the price around the highway, especially for the northern parts. So how do we get these interesting results? Our main method is to use predictive modeling to make scenario simulations. We use all the original data in the baseline, which is the scenario 0, uses to select the features related to the property price, train the model, and analyze its performance. After that, we change the features based on our future imagination, run the model, and analyze the predictive results. Feature selection is the most fundamental part of a good model. As we mentioned previously in the highway effect analysis, the property's internal characteristic, location of information, and distance to amenities are all taken into account. In scenario 1, we treat the completed Chinatown stage as a new park that removes the highway, so we change the property's distance to the nearest park and distance to highway. For scenario 2, we have the Chinatown stage, more commercial services, and higher quality housing can all be introduced by changing zoning, land use, and category code. Then the internal condition improves accordingly. Considering the different perspectives of commercial and residential improvements, the feature alteration has different triggers and following changes. For commercial change, we consider the zoning permission. We focus on to convert the vacant or industrial land in commercial mixed-use zoning CMX to commercial zone uses with zoning CMX3 and residential mixed-use zoning RMX3. Residential housing is available for building in vacant or underused lands where single-family housing could be converted to multifamily with zoning RM. Other internal enhancements are similar for both uses. After testing various types of models, we choose random forest to predict property price based on these features. Since the model is trained on existing data, we can evaluate its performance by comparing it to real observed values. This solid line indicates the general performance of our model, indicating a general underestimation of the price. The predictions now are off by 30% off on average, which also means the difference between predictions and original web prices on average is $210,000. You may think that our model is not that good, but for our use case, we are more concerned about the general trend of how property prices will change in our study area rather than in the individual accuracy. So what we are most concerned about is the clustering of prediction errors, and luckily this is not the case. Certain predictions with high errors are distributed evenly in our study area. Let's explore them in detail. This property with an error of 4 times the observed value is located close to City Hall with a center city mixed-use zoning CMX5. This industrial multifamily housing is located in the north and close to the highway with the zoning IRMX. Its price is about $120,000 less than the previous Center City property, but still has a very high error. The single-family attached housing with a zoning RSA 5 for the north has a slightly higher price, but also has a 1.5 times prediction error. It seems like prediction error is related to zoning type. IRMX and CMX5 properties have very inaccurate predictions. These two types indicate low-end industrial housing and high-rise center city buildings, which means our model cannot predict these properties well for their uncommonly low and high prices. To call back on our users, for business owners and local residents, industrial and office building prices are not of concern. After removing these two zoning types, our model errors decreased by about $12,000. Using altered features and a reliable model, we estimated how property prices might change under two future scenarios. After the Chinatown stage is completed, properties with over 50% increase are seen near the highway and in the northern parts. In scenario 2, where zoning changes are implemented to allow more retail and multifamily housing, most property prices rise by less than 10% compared to scenario 1. This suggests a lower risk of displacing local people due to rent increases. However, there are clusters of properties where prices jump by more than 30%. You can see that there are the clusters. So this could signal future affordability concerns and may require government action.
So to bring all together here, we talk about the highway effects of Act 67.6. It creates a lasting division in land accessibility and the property value between the two sides. To under how future planning decisions could reshape the pattern, we built random forest model for predicting property sale price for both sides and explore 3 planning scenarios after stage, and also visualize to reveal where land use change and how sale price response. So what we found? We found we found scenario 1 stabilized price, but it didn't close to persistence north-south divide. And scenario 2 shows stronger market performance across both sides of the highway. Property near I-676 in both sides experienced smaller price declines and an overall increase in sale prices. But it also presents more pronounced imbalance price change between the two sides, widening the price gap between two sides. Based on the findings, we'll give our recommendations for further development strategies. Decision on land use is not just about the zoning strategies. We need to first go in deep to check whether the sites can actually support the new land use in terms of location, infrastructure, and market readiness. And next, the sale price of some commercial parcels on the south side near the highway increased a lot and form as cluster of increase in our scenario planning. So we suggest that prioritizing develop these areas first. Last but not least, we cannot ignore the north side, and since unlocking land value in north side will require more than zoning strategies, it definitely needs investments in infrastructure, better access, and essential service to mitigate the highway effects barrier. We hope this gives you some insights into our Chinatown stage project and to see how it shapes property sale prices and more importantly, how future planning can better support equity in the Chinatown neighborhoods. Thank you all for listening.
Thank you very much. Casey, I believe you're with us, right? Is Chris also here?
Chris got pulled into a mayor's office meeting, so he couldn't make it, but I am here.
Okay. Well, Casey, I'm glad you're with us. This is a fellow Penn lecturer colleague of ours as well. So and a graduate of the Weitzman School. So Casey, I'm curious as to what your thoughts and questions are for the team. The floor is yours.
Absolutely, thank you. So first, I want to thank all of the students in this group for the hard work that they did over the course of the semester. I think the results have come a really long way and are really wonderful, so thank you. I was interested in, when we were talking about this, we talked a lot about not just the highway effect, but park effects and looking at, in Philadelphia, how does proximity to green space, since that is such a concern for Chinatown, typically impact residential and commercial real estate value or rents. And there wasn't a ton of discussion of that in this presentation. I don't know if there was additional work on that in the back end that you could speak to and how that was incorporated into this analysis.
We have done some park analysis before, and in our linear model, investigating the distance to highway and the property price, we also incorporate the distance to park, this feature in our model. So our result contains, like, the closer to the park, it tends to have higher crime rates and lower commercial services. So our main takeaway in that part is that we want to add more commercial services around the park, around the stage. So that's the main takeaway there.
Thank you. And then I liked the narrative perspectives of the business owner and the resident and how you kind of worked that in to discuss the different interests or concerns that each would have. I would argue that in a neighborhood like Chinatown, the business owners would probably be as concerned with cultural continuity as residents. I noticed that that was something that was kind of brought up on one, but not the other. I think in a situation like this, that is a concern that is probably shared by all of those groups, and just wanted to bring that up and maybe caution against making that distinction, since I don't know that it necessarily holds true. And yeah, I guess you talked a bit about the IRMX and the CMX5 zoning throwing off the model,
Yeah.
the predictive analysis. And so when you kind of controlled for that, you saw can you repeat what that was? I kind of missed it. It was a decrease in the error or a decrease in the
it's decreased
error price.
The error of our prediction. It makes our model predict other prices more accurate. So because what we mentioned that there is because these two types are not the main concern of local residents from our point of view. So we think the model we have now, it predicts not that good, but when it removes these two zoning types, it predicts better. So it's better for our future prediction of the sale price.
Fantastic. Thank you. Those are the primary questions that I had. I'd like to let anybody else who has questions take over, so I'm not monopolizing the time.
Thank you, Casey. I have a question for you to start. And I think we'll only have time for a couple questions because we're getting close to 4 o'clock. But you built these scenarios to try to explore what the future might look like. And one thing you didn't talk about in your presentation, but I want to mention, is that you interviewed a lot of people and you did a lot of qualitative research about Chinatown. You interviewed Professor Dominic Vitiello. You interviewed Jeff Lynn from the Philadelphia Fed, who's written all these papers about highways. When you were thinking about what is a logical future for Chinatown after the stitch, you mentioned like, okay, well, there's more commercial here and whatever, and you had a lot to get to. Can you dig into that a little more about why you why you created this scenario, what it's about, and what we're supposed to learn from it?
Yeah, I think one thing that we wanted to communicate, maybe we didn't do as good of a job in this presentation, is that we wanted to look at the highest and best use scenario of using land as best as possible, the way like real estate or developers see it, seeing how much value we can get out of land, and kind of, so that's why we added this like more commercial development and conversion of single family to multifamily homes, because people want to get more out of the land. But it's kind of, I guess, a warning too of like when we do that, even though the Chinatown Stitch project was created to repair harms done to this community, if we go with this case, we see that the area in general becomes less affordable. And so we need some more policy in place to make sure that current residents can remain and thrive where they're at, and actually get to enjoy the added amenity of a park and open green space. So that was kind of the reasoning behind this second scenario, being this like commercial space. Yeah, I don't know if that answered your question.
Eric, can you, I guess I'll take the last one.
It's more of a comment than a question. I'd love your responses as well. So could I have your responses? Is maybe the question. I loved your maps, the visualizations. They were terrific. One of the things that struck me most about this project is that it's a predictive model, but you're talking about it and using it in ways that assume causal validity. So you're talking about how removing something changes something else. I'll just give a really simple example based on what you showed. 95 is always next to the Delaware. It's never not going to be next to the Delaware. You don't know like specifically what proximity to 95 relative to proximity to the Delaware is worth. You just know like kind of you can predict something well. And so when you take a model that's built, you know, in a predictive way where you're testing all sorts of variables, you don't really know what removing a highway might or might not do. So there's a lot of assumptions that are built into that. So I would encourage you to be very careful with your language. Language around effects, I think, are deeply problematic when you're using a predictive model rather than a causal model. And then similarly, when you're making these scenario predictions, I think you want to be a little bit more careful about what's actually happening, what the underlying assumptions are, and how kind of differences between what's predictive and what's causal might create issues. But like I said, I think this is wonderful. The visualization's terrific. The concept terrific. I think there's a lot of great work. Just any responses to kind of those fundamental differences between the types of models.
Could you repeat again? I didn't.
So, for example, a causal model would be trying to test what's the effect of building a highway, or what's the effect of removing a highway. Whereas a predictive model is just trying to say, you know, next to a highway, how much more is property worth? I don't care about things like omitted variable bias. I don't care about things like multi-collinearity. All I care about is whether I predict better or worse. All I care about is my error, and how well I predict in sample, how well I predict out of sample, and variances in my error term. If something is supposed to be causal, I care deeply about the specific parameter estimate. Is my parameter estimate about proximity to highways, is it correct? Is it causal? And it's fundamentally a different way to think about modeling. And I'm asking how that relates to your project.
I think before the predictive model, we built that model first to investigate the highway distance and the property price. I think that's the part that you said is different from the predictive model, right? So we built our predictive model. Our feature engineering is based on what we previously done in the highway effects analysis. Maybe kind of settle your concerns about it. Does that make sense?
I think also to add on to that, yeah, you're right. Like we're doing a predictive model and we're, seeing how different variables relate to our outcome of property prices. And that's like a limitation of our study. It's very much just like trying to conceptualize how these possible changes may be reflected in, or sorry, how changing these different features of the land and properties, proximities to different amenities may influence price. It is a weakness that it's not a directly like causal inference that we're trying to make.
I can follow up. I think what Eric's trying to say is that the distinction between your associative models and your models that have a little bit of an experimental setup where the language that you use there, I know because I've seen the models, is appropriate. This is associated with that. You need to make a clear distinction, I think, to paraphrase Eric here, when you're talking about that model versus the predictive models exist in another kind of universe where the way that you interpret the models or their function in terms of your storytelling is very different. So just to be careful with the all else equal this, this, and this, that is on when you're on the associative modeling side of the project. Is that a good paraphrase of what you're saying? Yeah. Okay. Okay. In the interest of time, I know we could talk about this till we're blue in the face because there's so much to this project, but I think we should move on to closing our event today. And I want to start by have a round of applause for our team here. Thank you. Okay, I should say that Chinatown project is one of the most unique projects that we've ever done here. Absolutely. So Chris from Otis came to us and said, I'm really interested in the effect that it has when you're a certain distance, 1 more meter away from a highway. We're not sure we understand what the ramifications of this highway are going to be. And then that is one of the most exploratory projects that we've had. So, and hello, Jeff, welcome. And Jeff from the Philly Fed provided interview and has written great papers on the subject, which I recommend you read. But I appreciate the work of that group because that is an extraordinarily difficult communication exercise to talk about these things to communities potentially, in addition to public agencies who have empowered you to do this project. Okay, so notwithstanding the fact that you still owe me deliverables, we're done here. You made it across the finish line, and I want to congratulate you. I would like it if everyone could please give a round of applause for our students. This is fantastic. And I think it's a good time to reflect very briefly on sort of what's been done here, not just today, but over the course of, for some of you, a year, for some of you, 2 and 3 years here. So I wrote a couple things down in preparation to do this, but I thought the DC Bike Group made a really profound statement. We should be frank about what data can and can't do, which I think is a key thing to understand when you come out of a program like this, that people expect you to just be able to do something magical because you can write this computer code and you can build an app and you are well educated at this university and so on. But that's something to always keep in mind. And I think it's particularly relevant given the state of the world and the state of the field that you are entering, where there's a lot of cynicism and fear about the use of data. So being a responsible practitioner and saying, here's what data can and can't tell us, here's what data can and can't do, is really, really important. And to know that, you need to think back about the first class that we had at the beginning of the semester where we said, a good data scientist must know the policy, right? And if you don't know the policy and you don't know the programs, people get hurt. And people are inclined to believe your opinion because they don't know what data can and can't do, and they think that you're a very talented and smart and well-educated person, as they should. But therefore, it is your responsibility to understand not just the engineering and not just the statistics, and understand the policy, the program, the domain. And this is real government efficiency, okay? Delivering benefit to people better, with less money, and with more sensitivity than before, okay? So I'm very pleased with the time that we spent together. I've really appreciated getting to know you and learning from you. I learned a lot from these projects, especially the last month where we say, I don't know the answer to that question. You're the expert. You read like 50 papers about this, right? So I'm really grateful for that partnership and the investment that you've put into your professors and your program in being a part of these projects. But I'm really excited to see what you do in the future. I'm really excited to hear from you when you're out there in the professional world and you're doing something really awesome. Please let me know. Please let Matt know if you need a recommendation, if you need advice, if you just want to have a coffee, anything, please get in touch. But you're no longer my students, you are now my colleagues. So how about we have a toast to you and your accomplishments. Congratulations. That's it. Dismissed.